This is the best technology that can scan inside of the Great Pyramid that are undiscovered features.
Do any of these structures that they're interpreting fly in the face of what conventional archaeology would think exists inside the pyramids?
All of it.
All of it.
All of it.
There is also electricity inside this.
Fossilized lightning through these iron veins. What is creating the lack of signature here?
There is something. I can't disclose it now.
Interesting.
Each pyramid is producing a specific chemical, and the sequence of these chemicals transforms one product into the next product into the next product. Industrial scale chemical manufacturing.
If we do have tubular structures, pillars, with coils wrapping around them that go a kilometer deep with a foundation underneath them, that's insane. That's huge.
Correct, yeah, and it's something that needs to be addressed. Because there's no physical way that these could possibly have been built. Period.
Then I'm going with aliens. Like how do we explain that? For over 4,000 years, the pyramids of Egypt have stood as some of the most extraordinary structures ever built by human hands. The Great Pyramid of Khufu on the Giza Plateau contains roughly 2.3 million stone blocks, some weighing as much as 70 tons, arranged with a precision that still astonishes engineers today. The first and most obvious question everyone asks is how these insanely large, sophisticated, and astronomically aligned structures were built in ancient times, before modern civil engineering. Archaeologists and historians have proposed several main theories. French architect Jean-Pierre Houdin suggests that an internal ramp spiraling within the pyramid structure itself carried the blocks. This is an idea that gained renewed interest after the Scan Pyramids project detected unexplained voids inside the Great Pyramid. Other proposals involve lever systems, counterweights, and complex lifting techniques hinted at by ancient historians like Herodotus. And then, of course, you have the Atlantean acoustic levitation crowd. Always a good time, and I can't hate on them. But the point is, all of these theories have serious issues with them and are incredibly speculative. And there's another, even more simple question we take for granted, and one that's probably even more interesting when it comes to the pyramids. Why were they built in the first place? The most widely accepted explanation is the royal tomb theory. Most Egyptologists believe the Great Pyramid was built for the pharaoh Khufu around 2500 BC as part of a massive funerary complex designed to help the king ascend to the afterlife. And the Pyramid of Khafre was of course built for the tomb of Pharaoh Khafre, Khufu's son. But no confirmed mummies or tombs of Khufu or Khafre have ever been found inside of the pyramids. And the interior chambers themselves are surprisingly bare. And so in the last few decades, some very alternative ideas have emerged for what the pyramid's true purpose may have been. One of the most famous of these comes from former aerospace engineer and Joe Rogan guest Christopher Dunn. Dunn proposed that the Great Pyramid might have functioned as an ancient energy machine. In his view, the pyramid's internal chambers, granite structures, and resonant geometry may have all worked together to generate power, possibly through vibrations interacting with quartz crystals inside the stone. Researcher Geoffrey Drumm, who runs the amazing Land of Chem YouTube channel, believes the pyramids weren't producing electricity at all. They were harnessing atmospheric electricity and producing hydrogen gas and ammonium-based compounds essential for metalworking and agriculture, something ancient civilizations needed.
And my hypothesis for the function of the Great Pyramid is that the hydrogen sulfide gas coming from this subterranean karst cave and tunnel system is the initial reactant in the chemical manufacturing sequence within the Great Pyramid.
According to Drumm, different chambers inside the pyramid could have served as reaction vessels, where chemicals like zinc and acid interacted, generating hydrogen through controlled reactions. These fascinating open questions, how and why the pyramids got built, became infinitely weirder in 2022. That's when a small team of researchers, led by Italian radar specialist Filippo Biondi and his engineering colleague Corrado Malanga, made one of the boldest claims in the last century involving ancient archaeology. Using a technique called synthetic aperture radar Doppler tomography applied to satellite data, they claim to have detected 8 enormous cylindrical tubular structures going beneath the Giza Plateau, possibly including large vertical shafts and chamber-like formations extending hundreds of meters below the pyramids themselves.
We are counting at the moment 4 plus 4 tubes that are descending underneath, and they are connecting the top, so the base of the pyramid, to something that is located at the bottom.
So tonight on American Alchemy, we are hosting a historic roundtable discussion between Geoffrey and none other than Filippo Biondi himself, the man who conducted the scans and created the method that derived the images of these large columns below the pyramids. The result was probably the deepest conversation that's ever been had on the structure and purpose of the pyramids, and the vast complex of subterranean structures that might lie beneath them. Modern disclosure might not involve modern technology, but rather ancient technology hidden in plain sight. Without further ado, probably the 2 best guests I could think of to explore the birthplace of alchemy itself, ancient Egypt. Please welcome this week's American Alchemists, Geoffrey Drumm and Filippo Biondi.
Ignition sequence start. How is this possible?
Nothing too unusual about that.
Their existence cannot longer be denied.
When we first started selling merchandise at AmericanAlchemyMerch.com, we had no idea how complicated and annoying selling merch could be. We talked to a dozen different platforms and companies, comparing shipping tools, payment options, website builders, and it all felt like way more of a headache and complicated than it should be. We decided on Shopify, and within days, our store was up. Everything was running cleanly in an automated way, so we could just focus on the brand and the vision we had for it. That's when it hit us. Ideas don't scale on inspiration alone. They need a structure, a container. Shopify provides that structure. It quietly powers millions of creators and brands, about 10% of all United States e-commerce. From big names like Gymshark and Mattel to solo creators building from their bedrooms. Shopify made it simple to build a store that actually feels authentic to us, which matters when your brand lives in a niche like alternative tech, UFOs, or fringe science, and when you have a very clear brand vision. Plus, their AI tools help write descriptions, organize products, even clean up photos, so we can focus on what matters and what we care about, building the best custom merch line possible with the coolest designs, like our UFO cowboy tee and the Atomic Age tee. Plus, Shopify handles all of the unglamorous, more painful stuff: shipping, returns, email marketing, all in one clean dashboard. It's like having a silent partner who never sleeps. Our favorite part of the product is the dashboard, which gives us complete demographic information. We can see where our orders come from, making it easy to know who our most loyal, consistent customers are around the world. That's just one example, but Shopify really makes your life easier. Bring your next idea to life with Shopify quietly handling everything behind it. Sign up for your $1 per month trial and start today at shopify.com/Jesse. Again, that's shopify.com/Jesse, Jesse, for a $1 a month trial. It's just $1 a month to try Shopify, the state-of-the-art solution in e-commerce. I'm here with Filippo Biondi, round 2 with him, and I have brought in an amazing co-interviewer, Geoffrey Drumm, who I've become a recent big fan of.
Thanks, sir.
And I just can't wait enough for this conversation. I'm really excited to dive into this because Filippo, as we all know at this point, has, through synthetic aperture radar Doppler tomography, he's a scientist, he's a data scientist, 30 years PhD, who with his own method, the Biondi method, has basically figured out through these tomography scans, he's derived what he says looks like these 8 4+4 tubular structures with coils wrapping around them underneath the pyramids, not only actually underneath the pyramids, underneath some other structures as well. So it's kind of a bombshell finding. Obviously, it is also a really amazing meme that like took off on the internet. And Geoffrey, more recently, I've become a huge fan of just
Thank you.
because he's so rigorous, and I don't know too many people who have a step-by-step thesis as to what the pyramids actually their function is. You know, you're kind of in a league of your own. And so you know,
I appreciate that. That's a huge vote of confidence.
No, I mean it. I mean, it's you and Christopher Dunn. And so I'm excited to have you here because I think you can ask Filippo questions that I cannot.
Yes.
I think I probably accept a lot of things at face value. And so I'm really excited to host this discussion.
Yeah.
And thank you both for being here.
Thank you.
Thank you very much for your invitation.
So as far as kicking things off, why don't we just go over the core findings just for the audience's kind of context? So what are we talking about here when it comes to these synthetic aperture radar Doppler tomography scans? And if you could go into the method as specifically as possible, that would be very helpful.
Yes, the method is relatively new and not so, let's say, diffused by the other colleagues, colleagues of mine, but someone I know that is replicating the experiment, so I am very happy about this. Essentially, I worked a lot of years, maybe 30 years on radar and 20 years on radars installed on satellites. Synthetic aperture radar is an equipment that synthesizes a so-called integration time along the orbit in order to have azimuth resolution, very high azimuth resolution. So it is very important for civilian application and other applications. Today is state of the art because it recasts also in the commercial activities, because there are companies that American companies and also European companies that are building their own satellites. They launch the satellites in the sky, in the space. And they sell data. So it is very simple to find synthetic aperture radar data, and what we do is we reprocess this data in order to, and this is the core of our method, in order to retrieve the superficial vibration of the Earth. This superficial vibration, we have to consider this vibration like the waves that we can observe on the border of the swimming pool. So those kind of waves contains all the information that it is given by the underground. So we do like that. We estimate the vibration, and then we perform algorithms that are able to retrieve tomography. Tomography is we look inside.
It's slicing of the interior.
Yes. And we use acoustics, because acoustics in the acoustics are very important because they propagate only in matter.
Yep.
And we use as a carrier the light.
Yep.
Because in this space we don't have matter. We have, but we don't have matter, and we use the light. It means the radio frequency in the 10 gigahertz in the 10 gigahertz central frequency, so light, to carry the information of the vibrations.
Right.
So basically, you have synthetic aperture radar, which is a tried and true method. Nobody's arguing with, synthetic aperture radar being effective. You have companies like ICEYE, Umbra, Capella Space that work off this method. They use it for defense and commercial purposes. It's basically a higher resolution radar. And then I think the big update here is the Doppler tomography. Yes. And then the other update is you're getting these tomography scans, and you have software that is proprietary to you, right,
It's
Filippo?
proprietary to me because we have a patent that now I am also submitting a second patent
Mhm.
on the first patent because I made some improvements of the technique, and so I'm in these days we are submitting in United States.
So the two big updates are the Doppler tomography, and then you get the tomography scans, and it's your interpretation of the
Yes.
tomography scans, which
Yes,
is kind of this unique thing
yes.
to you. And so that has the world, up in flames, the archaeological world,
Yeah.
where you have, people like Flint Dibble coming at you and saying,
What a nice
why-
guy, right?
Yeah.
yeah. And
Hello, Geoffrey.
Geoffrey really struck me as somebody who, was asking, I think, one step level deeper questions than I could ask about this. And so I kind of want to, just maybe defer to you here
Sure.
as far as, what you think about these claims, because on the face of them, if we do have tubular structures, pillars with coils wrapping around them that go a kilometer deep with a foundation underneath them, that's insane. That's huge.
Correct. Yeah. And it's something that needs to be addressed. So to preface sort of my perspective on the new SAR scans, my work focuses on a comprehensive overview of the function of the Egyptian pyramids. From the Step Pyramid, Red Pyramid, Bent Pyramid, Great Pyramid, Central Pyramid, Final Pyramid, and also encompasses ancient structures like stone circles, passage chamber reactors, Teotihuacan, Japanese pyramids, etc. And it's a comprehensive overview of the function of these structures with a basis on mechanisms of operation related to physics and chemistry, with the function of the Egyptian pyramids being for industrial scale chemical manufacturing, where each pyramid is producing a specific chemical, and the sequence of these chemicals transforms one product into the next product into the next product. So, from my perspective, in interpreting and reverse engineering the function of the Egyptian pyramids, we have a known chamber configuration, which inherently any hypothesis on the function of the Egyptian pyramids has to specifically assess all of these specific components in the known configuration. So if there are new components, for example, a lot of people don't know that Filippo and the SAR team actually published their first paper back in 2020 when they scanned the Great Pyramid. And this paper did not get a lot of attention at the time. And I think a lot of people haven't gone back to look at your original research. And I'll also do my best to kind of summarize in layman's terms how the Biondi Protocol works in relation to the existing SAR satellite radar technology, because this is a conjunction of existing satellite technology with new software that's known as the Biondi Protocol that, again, is interpreting micro vibrations, which you term as phonons, as indicative of internal chambers within the structure. And we'll walk through this process. And I think the impetus for this, as you can see here on the screen, anybody who's watching, the organizers of the SAR team's first international conference was in Malta back in June of 2025. And the organizers of the conference were familiar with my work. Armando and Filippo were familiar with my work. And my wife and I, as you can see there, we had an absolutely spectacular time in Malta. It is gorgeous there. Such a fun conference. We got to meet everybody. And Filippo and I had a really engaging sort of question and answer process going on during this conference, where that was really why I was invited by the organizers of the conference to come and ask questions based on my knowledge of the existing configuration. And Filippo, you're the man when it comes to SAR technology, and you are the creator of this Biondi protocol. So whether you like it or not, you're the only person that has the qualifications to answer these questions.
You, Geoffrey, ask me the question.
Yes, of
If
course.
we can answer, we will answer.
And
Right. Yeah.
I want to say one thing, and then I'll defer
course,
to you,
yeah,
Geoffrey.
yeah.
I am
because-
here purposely.
Because if
Yeah.
I do think it's important, because a lot of people, the information space in podcast world is not always the best. And I think a lot of people might Google or ChatGPT synthetic aperture radar and get a quick debunk, like, oh, you can't penetrate the Earth with synthetic aperture radar. And I do think it's
that
important.
is ignorance.
Yeah, it is. It is. So this is really important that what you were saying is that there is a kind of phonon to photon conversion, and that these micro vibrations, just like you might be able to read the substructure underneath water through measuring the waves, translates to the electromagnetic radio waves that get translated to
into the satellite.
Into the satellite.
Correct. Yeah.
Exactly.
But penetration is related only to the information, the entropy.
Yep.
Which is the basics of information. I suggest everyone to read the mother paper of information, which is the paper of Shannon and
Claude Shannon.
And
he's the best. And also to back you up, there are other modalities, like there's something called cold atom sensing and gravitometry, which is non-invasive, above the surface, and you are measuring subsurface stuff. You aren't measuring it with perfect accuracy. So that's what's very important. And the reason I'm so excited to have you here is because I think a lot of the first order debunks, like the one I just mentioned, suck and are easy. They're ignorance, as you said. I think, and I don't even want to call it a debunk because it's a friendly conversation. But you have thought of other kind of interesting ways to poke at,
it's just objective questions out of fascination and interest for the work. And I think that's an important thing in science, is when people with different opinions come together, it helps us get closer to the truth.
Because diversity builds new things.
Of course. And I will agree, there are absolutely things below the Giza Plateau that we do not understand, that are the impetus for the construction of the pyramids on the Giza Plateau. They chose the Giza Plateau for a very specific reason. There are very important resources below the Giza Plateau that are directly related to the function of the Egyptian pyramids. So we'll kind of get to that at the end, but let's dive into this. So that everybody can just kind of hear. I'm going to read briefly, just quoting the abstract of your first paper.
Just to say, I remember in the last interview that I made with Jesse when he came in Corciano, where I live, I remember that I said one thing. In the Giza business, let's say business, there is a crucial material that is common in everything. So it's water.
Yes.
Water. So I think that water is very important.
I agree.
In this business.
And for example, we've actually taken samples of the water in the Osiris shaft, and I had that tested in conjunction with an archaeological project that I'm a member of called the Osirion 7 Archaeological Mission, in conjunction with Jim Westerman, to investigate the source of the water within the Osirion. So they're doing testing of the water in the Osirion and hydrological evaluation of the Osirion to try to determine why and where the water in the reservoir comes from. And there's also intrusive water in one of the central recesses that we're also trying to determine the source of this water. I'm an official member of that archaeological project, and I brought our water samples from the Osiris shaft to have tested in conjunction with the samples from them. And the Osiris shaft is brackish water. It's not fresh water. And it's not seawater, it's brackish water. So brackish water is slightly salty water, not fresh water, not seawater.
In Italian, it's called the salmastra.
So partially salt water. So there's a very independent aquifer located directly below the Osiris shaft that is not connected to the Nile River. So for example, the Nile is way, way back from the Giza Plateau. And because of the high Aswan Dam, there's no more flooding of the Nile River. So the water level inside of the Osiris shaft has not fluctuated since the time of its construction. So there's an independent aquifer located directly below the Osiris shaft, and that system was designed to tap into that aquifer at a very specific level at the bottom of the chamber, which is why the chamber is still filled with water at the bottom of the Osiris shaft today. So there's pockets of independent aquifers all over the Giza Plateau, and there's also subterranean flowing water, which
so there is also subterranean
moving water.
moving
Yeah.
water.
Yeah. So there's actually pumps
Okay.
that have been installed near the Valley Temple. So the Khafre Valley Temple near the Sphinx enclosure, the Egyptian government has installed pumps to try and pump this water out from below the Giza Plateau. So there's pumping stations at Giza where they've been pumping out this water from below the Giza Plateau, which is, there's a reason they're doing that.
Back in the day, I used to chug coffee like I was prepping for a quantum jump, but then I'd crash like my nervous system got slingshotted through a kaleidoscope. Anxiety spiking, aura flickering, and REM sleep never met her. It was like drinking battery acid on an empty stomach. Then I found mud water. It doesn't fry my circuits or my synapses. I use Mudwater's original blend over ice. It still has a little bit of caffeine, but it's stacked with adaptogens and nootropics like L-theanine, chaga, lion's mane, cacao, the whole Earth squad to keep you naturally energized and to ensure that you don't wake up with the morning scaries. One sip of Mudwater and my cells report for duty. 2 sips and boom, I'm plugged into the fungal Starfleet. All systems go. So, are you ready to make the switch to cleaner energy? Head to mudwater.com, that's MUDWTR.com, and grab your starter kit today. It's MUDWTR.com. Right now, our listeners get an exclusive deal up to 43% off your entire order, plus free shipping and a free rechargeable frother when you use code Jesse at checkout. That's right, up to 43% off with code Jesse, that's Jesse, at Mudwater, MUDWTR.com. After your purchase, they'll ask you how you found them. Please show your support and let them know we sent you.
It's from a sense of archaeological preservation, of course, which is the main justification for everything done in Egypt. We're trying to preserve the monuments. So we want to remove all the water.
So they installed pumps to remove water because they already know that there are structures inside.
Not necessarily that they know that they're structures, but it's more for the preservation of the pyramids on top to prevent more erosion from below. Because there is, and I'll get to this at the end of the conversation, they know for sure that there are caves and tunnels below Giza.
There are a lot of caves.
A lot of caves, which are natural geological features.
And then we will speak about this.
Yeah, of course. Yeah, and we agree on that, right?
Yeah.
We all agree on that. We all agree that the pyramids were likely not conventional tombs. Right?
Yeah.
So we're all like same page there. And then it sounds like we're on the same page that water is this important thing, whether it's chemical power plant or, energy power plant. But yeah, what are you saying?
And we are sure also that they were not built by the Egyptians.
That would be my bias. What do you think?
What do you think?
So built by the Egyptians, I think they were built by the civilization that lived in Egypt during a period known as the Saharan Humid Period, which is from 8500 BC to around 5300 BC.
Which predates what Zahi Hawass and like the Ministry of Culture would say.
And during that time period, the Upper Eastern Sahara was being transformed from a desert into a vast area of farmland by sweeping monsoon rains. So there was tons of rain, there was tons of water, there were tons of thunderstorms, which is also directly connected to my hypothesis on the function of the pyramid structures. Directly connected to thunderstorms and lightning, which we'll get to the power source of the pyramids and why these subterranean structures might be important for capturing and recirculating that electrical current.
And you have what seems to be water damage and erosion on the nose of the Sphinx that people like John Anthony West talk about.
Yeah, the back of the Sphinx enclosure.
Okay,
Yeah, the
interesting.
water,
Not in the noses.
the water
Okay.
erosion at the back of the Sphinx enclosure.
Okay,
Yeah,
okay.
that's the work of Robert Schoch that looks
Robert
at those
Schoch as well.
vertical fissures on the back of the Sphinx enclosure, which is indicative that the structure was built during a time period where there was significantly more rainfall.
Right.
So I think it was built by the Egyptians by virtue of it being the people that were in Egypt
Yeah, sure.
at the time,
Yeah.
which predates. So I do think it was. So I'm not in the alien camp where I think that these are extraterrestrial. I think they were built by human beings at the end of the last ice age in order to reestablish and rebuild humanity after the largest cataclysm that basically destroyed most of the planet and put human beings at risk for extinction.
Yeah, I mean,
So they're infrastructure projects.
you mentioned Robert Schoch.
Yeah.
You know, he and Graham Hancock would say that the Sphinx itself is actually an homage to, you know, the former procession.
Sure.
And that, you know, the constellation Leo, which was, you know, facing true north, was what it was, you know, pointing towards, and that the pharaonic, you know, headdress is actually sort of retrofitted
Yes.
onto it. Would you agree with that? Or
So I think the Sphinx itself is a dynastic monument that was built on an existing bedrock outcrop within the Sphinx enclosure.
Okay. So similar to what
Correct.
they
Yeah,
think.
yeah.
Okay. So
I don't think the Sphinx monument as a statue is contemporary to the pyramids themselves. Two separate time periods.
Got it. Yeah, no. So it sounds like we're all on the same page that the conventional archaeological explanation for what's going on is kind of prima facie wrong, and that the goalposts are clearly moving on that.
Let's say that we are sure that when I open the history book, school book of my son, and I go to the pyramid and I read to 2500 BC is not true.
Yes, exactly.
So let's get into it because I have some technical questions. So the title of their first paper. Again, when I read this at first, I was like, what the hell is going on here? Synthetic aperture radar Doppler tomography detects undiscovered high-resolution internal structures of the Great Pyramid of Giza. So this was their first public scan of the Great Pyramid before they scanned the Khafre Pyramid, the central pyramid. And I'm going to quote briefly from the abstract here, and then I'll do my best to, you know, from a layman's interpretation, provide an explanation for exactly what's happening here for people who don't understand the technical stuff. So one problem with synthetic aperture radar is that given the limited penetrating effects of the electromagnetic waves
And
inside
we are saying
solids.
one of the problems.
Yes, yeah.
So who says that? I'm sorry if I interrupt.
It's okay. Go ahead. Yeah, please.
Who says that? Who says that? No, it's impossible because radar can't penetrate. This is the main issue.
Correct. Yeah. So I'm just
We are going to dealing. With
Yeah,
the main issue.
and
It's
in
written
the
down
paper, this is in the abstract. They're proposing one of the main problems.
Yeah.
And then the resolution to the problem is the implementation of your new software system. So again, let me just, so people can understand what's going on. So one problem with SAR radar is that given the limited penetrating effects of electromagnetic waves inside of solids, the capability to image inside distributed targets is excluded. So under these circumstances, imaging activity is only given on the surface of distributed targets.
Absolutely.
This paper describes an imaging approach based on the investigation of micro movements on the surface of the Khnum-Khufu Pyramid, the Great Pyramid, usually generated by background seismic waves. So essentially what the technology and the Biondi Protocol is, again, Filippo, please correct me if I'm wrong, and then agree if I have this interpretation correct.
Yes.
So we have existing synthetic aperture radar satellite technology. And what you've done is developed a new software that works in conjunction with these existing satellites to detect micro movements on the surface of the structure, which you have termed as phonons. And those phonons and the differences between the structure and the cavities are indications of chambers and hidden structures inside of the pyramid.
Everything is encoded on these micro movements. Because
correct.
If you have a chamber, the micro movements are like that.
Right.
If you don't have the chamber, the micro movement movements are different,
Correct. Yeah.
present on the surface.
Right.
Okay.
Yeah. Yeah. So again, this is the whole revolutionary and novel approach of the Biondi Protocol is it's utilizing these surface micro vibrations to tell us what's going on the inside of the
Yes.
structure.
Absolutely,
So
yes.
again, to clarify, there's been some discussion in the community that, SAR technology is old and it's vetted. It is 100%. SAR technology has been around for a long time, but what Filippo has done is developed a new approach to use these existing satellites.
Existing data.
Correct. Yeah. To do
Existing
something a
data.
little different.
Okay.
Right. So we're now going to be using these micro vibrations, which again, they've called phonons, is the term utilized. So again, if you're reading the paper, if you're hearing a technical discussion, when you talk about phonons, you're talking about these micro vibrations that are being detected by the radar.
Yes.
Okay.
I please ask you to go a bit up and at the previous slide, please. On the abstract.
So I have some, this one here. Yeah. Yeah.
And there is written very clear that Khnum Khufu becomes transparent like a crystal when observed in the micro-movement domain.
Yes.
It's written there.
Yeah. Yeah.
Based on this novelty, we have completely reconstructed internal objects observing and measuring structure that have never been discovered before.
Yep.
The experimental results are estimated by processing series of SAR images. So this is the SAR. The SAR gives you an image, existing image, and then we process those images. In that case, it was the 2020 second generation Italian COSMO-SkyMed satellite system. A week ago, we put in orbit a third satellite of COSMO-SkyMed second generation. So now Italy has 3 satellites of COSMO-SkyMed second generation.
Yep.
It's very good.
And I'll show all of the images from this paper so people can see what you've discovered inside of the Great Pyramid and all of those diagrams.
Okay.
So this is from the Malta conference, which fast forward a couple years later, we're in Malta. And this just gives some additional information for the people watching so they can understand when we say phonons, they'll understand that those are the micro movements.
Phonons are micro movements.
Correct.
When we deal with light, light is composed by photons.
Correct. Yeah.
The vibrations of this table at any frequency is a vibration of the matter, and the vibration of the matter is composed by phonons.
Yep.
Okay.
Yeah. So in this slide here, and this is where I have some questions about the process of the radar scan itself. So you have
I'm here to explain everything about this everywhere.
Yeah, of course. So the satellite is going around the Earth.
Yes.
And the flat Earth people are going to go nuts when I do this, right?
No, there is the Pac-Man theory.
Right. Yeah. So again,
the satellite goes.
It goes around like this.
Goes outside the Pac-Man theory, and
it comes back around. Yeah, magically,
that's crazy.
Right? So again, the satellite is going around the Earth, right?
Yes.
And you're making passes over the target object.
Okay.
So the satellite's going around like this, and you're imaging the Great Pyramid, for example.
Yes.
What is the square footage?
The square footage
or the square meters, the footprint on the ground.
Okay.
Yeah,
that's the correct word.
Yeah, what is the size of the area of the target scan for the radar?
5 kilometers times 5 kilometers.
Okay. So is that a standard footprint? Or can you adjust the size?
It depends on the so-called geometry.
Okay.
There is a law that that belongs on radar.
Yeah.
The more the resolution, the less the footprint.
The more resolution, less footprint. Right. Yeah.
Okay.
Because the smaller the footprint,
the
more accurate
dense
it is.
Information inside the small. It's like a light. When you focus the light, the footprint on this table.
Yes.
So if you focus the light, you have more information inside the footprint.
Right.
Okay.
So you also use the phrase tomographic line.
Tomographic line,
which is a slice
of
the internal
Yes, and
system.
you extract a vertical curtain.
Correct. Yeah. So to create these scans, the
Yes.
raw data,
Yeah.
how many times does the satellite go around and over the
No.
target object? So it's only one
15
scan.
seconds.
15 seconds.
Of integration.
Okay.
It is in the signal processing language a sufficient statistic.
Okay.
Or have a tomographic analysis. You can use also series of interferometric data.
Yep.
I have to explain what is an interferometric data. It is you are observing this target here. The satellite passes. You catch a snapshot of this target.
Yes.
When the satellite goes another time on this target, you will never see it in the same geometry. It means same incidence angle, because the Earth is moving while the satellite is
Sure. Yeah.
is turning around the Earth.
Right.
So you have to wait the so-called orbital procession. Orbital, I don't remember the name, but orbital. Then after I will remember it.
Yeah.
That in COSMO-SkyMed is 16 days. You have to wait 16 days in order to observe the same target in the same geometry.
Yeah, that was going to be my next question.
And there you can collect 15 seconds, 15 seconds, 15 seconds, 15 seconds, 3 months of observation persistently on the target.
Yes.
And you can collect n times 15 seconds of observation.
Right.
But one image is a sufficient statistic in order to retrieve tomography.
Okay. So that was actually my second question was, are these composites of multiple passes and then all of them are put together for one image?
Why you are speaking about multiple passages? We said that one image, 15 seconds of integration, in order to perform the synthesis of the image is a sufficient statistic.
Right.
So with 15 seconds, you have an image.
Okay.
Look.
And that's So just to clarify again, I'm just curious about how the process works. So the data shown in the first paper and in the scans of the Khafre Pyramid and the pillars below, that's collected from a single scan, 15 seconds.
With a single synthetic aperture radar image.
Okay.
15 seconds of integration.
Yeah. So we'll talk about the scans of the Osiris shaft as well.
Also that.
And that's why, you remember, I went to the Giza Plateau to investigate the area around the Osiris shaft.
Yes.
And this is when I was asking you about the footprint, the area of the scan.
Yeah.
So when you scanned the Osiris shaft, was the footprint of the area in terms of meters by meters, length by width, was that also 5 kilometers, or did you make the scan area smaller?
We used only one available product of synthetic aperture data given by COSMO-SkyMed, which is called Spotlight 2, the civilian application of COSMO-SkyMed.
Okay.
And that ensures 5 kilometers times 5 kilometers in that resolution.
Okay.
And the space resolution is submetric, nearly 1 meter plus 1 meter.
Right.
1 meter times 1 meter.
Okay. And I'll show the scan data from the Osiris shaft. And the reason I'm asking about the footprint is because it's a 2-dimensional image.
Yes.
Right?
Tomographic line times depth.
Correct.
Okay.
So you're taking a 5 by 5 kilometer scan and compressing it.
No. You choose the pixel that you want to invert.
Okay.
You can choose any pixel.
Right.
The image. Maybe you choose. This is the image. Okay. You choose this pixel and this other pixel. You draw a line and you extract the vertical curtain.
Okay.
You can go anywhere on the image. Okay.
Interesting.
Okay.
And the reason I'll get to it when we look at the scan data.
Yes.
Because on the left side of the Osiris shaft, it's picking up something else there.
Yes.
Yeah.
I tell you this.
And that's why I was
I tell you this,
interested.
it's
Yeah,
very
because we're on the
important,
same.
this.
Yeah, of course. Yeah,
Thank you for this question.
of course.
Before we get into that, can I just say one thing? Because
Yes,
we're scared. The Osiris shaft is used often as evidence by your team
yes.
for at least some validation. It's
There
not
is a
blind validation
because we know perfectly
because you know the
shape.
structure
Yeah.
and you used this same method
Yes.
to derive that structure.
Yes. Indeed, I
And-
like to show the Gran Sasso laboratory because it's very nice in my personal opinion.
Well, there you go.
Yeah, I have,
also the Grand
I have
Sasso
that too,
Library.
so we can show
Yeah.
everybody the proof of concept.
Mhm.
So
There's the
again-
Gran Sasso laboratory. You see also the interferometer that is at the end of the structure.
Yeah,
You
yeah.
see it.
and I thought those
Right.
proof of concepts. So again, it's proof of concept
Yes.
to establish the precedent and the viability of the technology.
Yes.
To scan existing structures where we have a known configuration. And this technology was very good at accurately detecting the known structures within these modern facilities that were scanned.
But also the Osiris shaft too.
We'll talk about that. I have a question. I just have some questions.
I've learned some hard-earned lessons in life. For example, I've learned the hard way that comfortable clothing usually means comfortable for 15 minutes and then spending the rest of the day subtly irritated. The rough fabric, the chafing, the lack of flexibility, it all just sucks. That's why I've been wearing Chubbies. Their everywhere pants are the rare pants that actually move with you. They've got real stretch, the elastic waistband is genuinely comfortable, and they still look really put together. I'll wear them on a recording day, running around doing a million things, and I'm not thinking about my clothes at all, which is kind of the point. Same with their shorts and swim trunks that I have right here. They're lightweight, they're stretchy, they fit just right, and you're not dealing with that old scratchy mesh situation down there. You put them on and you're done. For a limited time, Chubbies is giving our listeners 20% off with code Jesse at chubbiesshorts.com. That is 20% off your order with code Jesse. Give your thighs the VIP treatment they deserve with Chubbies. Support our show, use our code, and tell them we sent you. Thank you so much to Chubbies for sponsoring today's episode.
I imagine the question that you want to ask me that we will arrive.
Yeah, yeah.
Yes, but I anticipate you that any measurement, technical measurement, is affected by errors.
Errors, right, of course, yeah.
So
So
if you have something and aberration,
Yeah.
because you
Correct.
are watching in a crystal that it's made of stones, no? Of
Yes.
stones. You can have aberration on the results.
so
And that's very normal.
background noise
Background noise and also aberration.
and interference.
What is an aberration?
Yeah,
An aberration is due by the not constant density of the matter.
sure.
While you are dealing with vibrations penetrates inside the matter. But the matter, vibrations are travels matter with a speed that it depends on the density of the matter in where they are traveling.
Correct.
So if the matter is not has different densities, so you have aberration on the results.
Sure. Yeah. Yeah. So to reinterpret what
Yeah.
he just said is the penetration and the signature of vibrational analysis
Yes.
depends on the density of the material,
Yes.
because the more dense the material, the less vibrational signal.
The velocity changes.
Correct.
So you have interference.
Sure. Yeah.
Huh?
Yeah.
Okay.
And real quick,
Go ahead.
just for the audience, because I want them to kind of visualize and have context for this.
Yeah.
Why don't you answer? What is the Osiris shaft?
So the Osiris shaft is a 3-level structure located on the eastern causeway leading from the central pyramid down to the Valley Temple and the Sphinx. And it's 33-meter underground triple chamber system. Not triple chamber, 3 different levels. You have a shaft that goes down to the primary level. You have another shaft that goes down to the secondary level, where there's 6 housings that have some containers of different material. One's dacite, one's black basalt. And then you go down to the third level where there is 4 pillars. This is the area that's tapped into that subterranean aquifer. It's literally calibrated to just tap the surface of the water in that underground aquifer. And there's another container down in the third level.
And what is the Gran Sasso Laboratory?
Yes, the Gran Sasso Laboratory is located in 1.4 kilometers below the earth, starting from the apice of the Gran Sasso, the top of the mountain, and it is very huge, very very big, and it is always in alive. It means that there are ventilators, there are facilities, electrical components inside, so it is in alive.
What are they? Is this like
it's a physics lab.
So it's like
Yeah,
it's like one of the
physics lab,
national labs in the U.S., like Los Alamos,
Yes,
or Lawrence
I tell you
Livermore, or something like that.
what is the principal core of the Gran Sasso. It is called the Gerda experiment because they didn't find it, still find it, the so-called Majorana particle.
Mm.
The Majorana particle is very important because it demonstrates that there are particles that are antiparticles of their self. Okay, and so in the Gran Sasso was made purposely to demonstrate the existence of the Majorana particle.
The existence of antiparticles.
That is antiparticle of him. So particle and antiparticle are the same thing. And so that opens a lot of things.
So like, because now in particle
in-
theory, now you have electrons and positrons. But what exactly are you saying?
But we are dealing with neutrinos.
Well, like quarks and
Yes, and neutrino.
oh, you're literally neutrinos.
Yes.
Okay, yeah. So neutrinos,
Subatomic,
yeah.
subatomic particles,
yes.
and neutrinos, for people that don't know, are very hard to detect. They're
Yeah.
very elusive. So, and they seem to
Yes.
penetrate through all.
And so,
yeah.
yes, they built the Gran Sasso Laboratory in order to have a stable environment, very silent environment, because there is all the mountain that makes as a filter. And
It's an
so
insulator for the detecting
yes.
equipment. They built it inside of a mountain.
Yes,
Yeah.
and there is a specific detector that has been built in order to recognize this Majorana particle.
Very cool. Okay.
Yeah. And I'll show that in just a second so people can see the scan of the lab.
Sweet.
So again, I'm just going to introduce. We talked a little bit about the abstract,
Yeah.
the development of the technology, and how it was implemented in this first scan.
Yeah.
So what we're looking at here is one of the first.
Yes, this was the first one.
Yeah, the raw data
It's
images.
a bit noisy, but
And-
the technique
Yeah,
proved it.
yeah.
This is what this
So Filippo, you kind of already know my questions. looking at it,
Okay, you
because
recognize.
because now
Okay.
you're 6 years removed from the first paper, and from what I understand, the satellites that you're using now are superior to the ones that you were using during this initial scan, and now you're
The
using
algorithm is superior also.
and now you're using multiple satellites where this one was only collected with a single satellite. Is that
Yeah.
correct?
Yes.
Okay.
Absolutely.
So what are we looking at here?
Yeah. So basically here on the left. So let's start with on the right.
Yeah.
On the right is the raw scan data image.
Mhm.
On the left is an overlay of the configuration of the Great Pyramid,
Yeah.
overlaid on top of the tomographic results.
Yes. I have
So-
to make a remark. When
Yeah.
you speak about raw data,
Yes.
these are dealing always with focused data.
Yes.
Because also in the vibrational domain, you have raw data and focus data.
Yes.
Okay, so raw data is the data that you have before the so-called fast Fourier transform. I tell you, if you have a camera like that camera, and you make a picture with that camera,
Mhm.
you see the image.
Correct.
Okay, if you disassemble the camera and you separate the optics by the body of the camera, you can make a photo also with using only the body of the camera. The result is that you see a picture, but you don't see the picture focused, because the focusing procedure is
So
done
like
by the optics.
developing the image.
Yes.
So a comparison to photography is like old cameras where you have to develop the photo. The photo is there,
Yes.
but it requires a process to
Yes.
focus the image.
And in that case, the process is made naturally by the lens, because the lens performs Fourier transform
Okay.
of what you are seeing.
So is this image on the right, is this not focused?
Focused.
It is focused.
Yes.
Yeah.
Okay.
So it's
got
the
it.
process.
It's the process.
yeah, so they
not
take-
raw data,
but
it
the
is
focus
tomograph,
data.
The vertical curtain.
And when,
Yeah,
when you
okay.
use the Biondi method with your software, are you using an inversion of the focused data
of the
or
raw
the raw
data.
data? You
Raw
use
data
the raw
are
data.
inverted.
Yeah.
That's interesting.
Yeah. So this is the final
Okay.
product
The final
of what you actually want to look for.
No, that's called
No.
final noisy product.
But you use the unfocused raw data.
No, we don't have to confuse the SAR image, so
Yeah.
the optical image, with what we are retrieving on the vertical curtain. Also, when we retrieve something, when we extract the tomographic line, also there you have raw data, and you have to focus it also.
Got it. But
You have to focus everything. Any instrumental measurement equipment that makes photo, you have to focus this photo.
and you have to focus it before you use your Biondi method, or is it after?
So the Biondi method itself is what receives these micro vibrations.
Got it.
So then that raw data that receives those micro vibrations is processed to create this focused image.
So there's nothing
So
particularly unique or proprietary about turning the focused SAR data into an image. Is that
No,
correct?
Yes, it's
That's
it's
just very
it's
basic.
his
conventional math.
proprietary process
Got
is
it.
just the retrieval of the micro movements
Makes sense.
that allow this imimaging to be possible.
Yes.
Okay.
Right.
Just to remark the fact, the Biondi Protocol is composed by two steps.
Mm.
The first step is called synthesis, and the second step is called analysis.
Mm-hmm.
In the synthesis, we retrieve the vibrations
Mm.
on the pixel composing the tomographic line that we want to invert. The second process is called analysis, the inversion, which is a fast Fourier transform, the lens of the camera, because you see nothing.
So again, this is a good
Yeah.
preparation for everything that you're going to face coming up, because now the work is going to get even more popular.
Sì, sì.
And you're going to have more people asking questions like this that are trying to better understand.
Sì.
So moving forward, so people can understand what they're looking at with the next set of focused images.
Yes.
Here on the right, we have the scale.
Yes.
So this is the concentration or intensity of the vibrations.
One normalizer.
Correct. Yeah. So you see everything in blue is the normal body of the structure or the background air, etc. Right? So as it goes up the scale, we have more intense vibrations that are being registered by this satellite radar. It's just so everybody can understand the coloring.
Correct.
Yeah, correct. Yeah, it just shows the intensity of the vibrations that are detected. So looking back on it, are you still confident and proud of this data?
Absolutely.
Or would you
yes.
rather go back and try to clean it up more?
But yes, we can manage to clean it up more. Absolutely, yes. But these results gives you a lot of information.
Right.
But we didn't use only one result. We had a plethora of results in order to retrieve the 3D that you will show.
Yes, I have everything. Yeah, yeah.
I have to say something about my technique that we have to, when you extract a vertical curtain, it is normal that...
So you're saying vertical curtain.
Curtain, yes.
Curtain.
Yes.
Right. So like the sheet or the layer or the slice, the vertical curtain.
Like
Yep.
that.
Okay. Yeah. So just in case people didn't understand, vertical curtain means the slice that's being extracted from this.
This is important, that the vertical curtain is not perfect. Maybe if a very bright target is located here, you can see it. You have to move a lot the vertical curtain in order you don't see it again. Because it's like a cone of sensitivity. Because every antenna has a cone of sensitivity.
Yes.
So if you are perfectly in the line of sight, okay, you will see things that are mainly located on the line of sight.
Yes.
But if you have bright targets that are located also having a certain angular of deviation, you can see it.
Yeah, and we'll talk about
that is what happened there. What you will anticipate me in the questions of the Osiris shaft is true. You can see also things that are located here.
Yes.
Here.
Right. Exactly. Okay? Yeah. And we'll talk about this cone of sensitivity when it comes to the muon scanning.
Hey, also there you have things, because also there they have raw data. Also there they have to perform fast Fourier transform. I know everything about it.
So I included some so we can get your opinion and feedback.
Yes.
Because so for people that don't know, muon scanning is using cosmic ray absorption to do a similar process to detect interior structures.
They use that method like the camera, like my camera. You have to always focus data. You have to always perform fast Fourier transform. And you have to always perform tomographic inversion. Also there.
Yeah. So I have some information here about that, and I would love to hear your opinion on that, because they use...
It's a pleasure for me too.
Yeah, of course. And so again, my objective here is just to get to the bottom of it, because there's conflicting data between what the muon scanning team has reported and what your team has reported.
Yes.
So I wanted to get your interpretation for why that's the case, and then I'll show the data here in just a second.
Okay.
So we have 3 red squares.
There we have a focus at 3 for who is reading, no? So to give the readers a help how to interpret it.
Correct. Yeah. Okay. So on the far right, you can see the edge of the pyramid there.
Yes.
With all of that yellow and red, that is the surface external casing of the Great Pyramid, with all of that red and yellow, very intense vibrations, because it's closer to the surface.
I like it a lot. When you see it, it's very, in my best opinion, it's very nice, this result. Okay.
Yeah.
And we can
And then moving on the inside, we have 1, 2, and 3. 1 being the area around the king's chamber.
Yes.
2 being the queen's chamber. And 3 is the subterranean chamber. And here, I will say that the detection of the queen's chamber at 2, and you can see here the overlay of the queen's chamber in the center with the raw scan data. The queen's chamber always has a very good signature, a very strong vibrational signature.
Yes.
Right.
The queen's chamber is a benchmark because we can see it.
And it would also help you determining the most effective curtain or slice. So if you have a strong signature on the queen's chamber, you know that your tomographic line is lined up accurately for the objects of interest in the particular scan. In terms of the configuration, I'll show some diagrams, and everything in the Great Pyramid is aligned right on top of each other. So again, this just is showing the first overlay.
But I guess we'll go back there
for
a second. My sort of super stupid question is, like, I'm looking at the raw tomographic result. And I'm looking at 1, 2, 3, and maybe I see something a little around 1, but 2 and 3 look mostly like in the sort of blue range. Like, how do you convert one to the other? Like,
so let me explain here.
Is this a failure to detect, or is this a positive detection of the queen's chamber?
So let me clarify. So all of these images are screenshots directly from the paper, and here on the left is a standard diagram of the Great Pyramid. This is not one of their models, which I'll show their models here in just a second.
Okay.
Where they actually interpreted the focused scan data into new 3D models.
Okay.
So this is a known standard diagram on the left.
Okay.
Overlaid with the focused data.
Yeah.
And I would agree with that statement that 1 and 3, you can see the highlight, aren't super encouraging in terms of the detection in this particular slice.
Okay.
So for example, at 1, I don't see a clear signature there for the king's chamber.
Sure.
And down at 3, if you look at the overlay of the diagram on top of it,
Yeah.
it's not picking up the subterranean chamber either.
Yeah.
On the far left, you can't see a glow,
Yeah.
which is indicative of these vibrations from the subterranean chamber.
Filippo, do you agree with that? Or like, do you agree that it's sort of missing the subterranean chamber and the king's chamber?
Yes, I agree.
Okay.
Yes.
Okay.
Yeah.
Yeah.
And so again, this just kind of establishes a
it's-
way for us to discuss this.
It is not mathematical that we can see in that tomographic line using that radar image that we can detect things. It's not mathematical, sure. We are not sure. So we have to do different measurements in order to have the results. Okay?
But I guess my, again, super dumb question, and I think I'm probably jumping ahead with it, is if we fail to detect certain chambers in the pyramid, why are we high confidence in structures going a kilometer deep underneath the pyramid?
Yes, because in the Khafre research that we made a few years later than this, we changed the approach. So we used very different geometries on the satellite data. So with very low incidence angle, that means that the layover of the radar images were very high. But that kind of acquisition, when we use low incidence angle, the power of the photons is very high because you see things like that. So you have a direct interaction with the Earth. That kind of increasing of power allowed us to see deeper. Okay. And in that kind of configuration, we were able to measure the structure that were underneath.
Did you ever redo the Great Pyramid and accurately detect these chambers with the lower angle of incidence?
Yes, this it was a medium angle of incidence.
So when you say the angle of incident, let me try to interpret that for the layperson. So when the satellite starts scanning, right, this 15 seconds of scanning time, the process starts lower as opposed to scanning up here. So you're scanning from lower on the horizon as opposed to trying to scan from the top.
I give you the answer about this. So we have to do a bit lesson now of how data are acquired. Let's say that this is the target. That I want to, this is 5 kilometers times 5 kilometers.
Which is a huge area to scan.
Yes. It's very generous.
Right.
I want a picture here.
There we go.
Okay. This is the satellite. The satellite flies on an orbit.
Correct.
Okay. A curved orbit. So if I want an image here, in the radar field, we say I don't want it squinted. So it means that the sense, we trace here a vertical line. We start the sensing here, minus 7 seconds, plus 7 seconds, 15 seconds.
Right.
7.5, 7, like that. So here we begin acting our sensing, and here we release the sensing. We have the image. But SAR is a side-looking sensor, so we have to tilt. This is the zero Doppler. Tack. We have to tilt on the incidence angle, because it's a side-looking. And we can scan, let's say, never natural, because it doesn't work. So from here, like that, to here. From here to here, like that. So we choose a very low incidence angle, which is the angle belonging the nadir of our image and the line of sight, this angle. This is the incidence angle. Low incidence angle, high layover, high incidence angle, low layover effect. And that now I tell you what is the layover. Like that to like that. For the Khafre research project, we used low incidence angle. Why? Because the photons that are transmitted here on the Earth has high power. Because the probability that the photons that arrive us here are retransmitted into the deep space is low. So you have the scattering energy is higher than this, that is lower.
Mhm.
Okay? Because we wanted to go inside, because we wanted to see targets very bright, because here the Doppler effect is more. We are more sensitive in the Doppler effect with low incidence angle with respect to the higher incidence angle. Okay?
Yep. And all of the validation you've done
Yes.
has been at lower incidence angle.
Yeah.
Okay. And so
Yes.
And-
lower incidence angle is better.
uh,
In this case,
yeah.
we wanted to see. We were focused on the pyramid at the beginning in 2020. And if we were using low incidence angle data, the pyramid are layovered. It means that, imagine the pyramid. You see the pyramid. The pyramid is smashed on the layover. It means that you see the pyramid like that.
Mm-hmm.
The pyramid is smashed like that, and so it is difficult to see details inside the pyramid. But we were interested in the recent research that we did on all the Giza Plateau to see, okay, the pyramid, I don't care about a lot about the pyramid. I want to see what there is below the pyramid. I don't know if I am understanding this, if I am explaining better this. So we principally used lower incidence angle, but not everywhere. So we used let's say different incidence angle.
Got it. And then you triangulated the truth from the
Yes.
different incidents.
Yes.
And are you highly confident that if you used the same methodology on the Great Pyramid again with the different incidence angles and triangulating them?
We did it.
And you
but it was not to retrieve things that we did on 2020, but it was focused to see what there was deep below the Kunum Kufu.
But did you ever?
I don't know if
it's super clear. Did you ever try to redo just the pyramid itself to make sure that the accuracy on the chambers was correct?
No, but we can.
But you can do it. Okay.
Yes.
So I'll also you haven't seen any of this yet. The first paper data. There's way more.
Oh yeah.
And they did.
There are a lot of results.
Oh yeah, of course. And I'm going to show all that so everyone can see it. I think it's important for everyone to see it because they did different scans that show it sometimes. So we'll get to that now.
Yes.
We can go ahead. So for example, this next one is this image from this same scan. It's just a focused image.
Yes.
Okay.
Something.
So this one, I think we would.
Queen chamber.
Yeah, down below.
Yeah.
Right. So I think we all agree that the imaging of the king's chamber here is not great, but we do have a very promising image of the queen's chamber.
Yeah.
I would say that this is actually, and you can even see, so look at C down there on the bottom right. You can actually see the horizontal shaft coming out of the queen's chamber is detected, I would say, fairly accurately. So I think this is, again, I kind of like to look at the positives and the negatives, right? Objectively analyzing the data.
Yes, Geoffrey, I tell you this. The importance of the future of this technique is the velocity of to obtain the result.
So the speed of the radar.
No, the speed of the synthesis. Okay. You have the SAR image. You have to perform. You have a tomographic line. You have to perform a synthesis. To perform synthesis, you need days and days, because it is time consuming. It's consuming the processing. You've been in Corsiano. I showed you the computer, big computers, but you need time.
Yes.
And the best thing to do now is to increase the speed, so decrease the time that I have to wait in order to obtain a tomography.
Okay.
And so to make it also, let's say, similar real time. What does it mean? That this the thing that I'm thinking. This is the procedure that I'm thinking that we will do it in the future. I think that the future of this technique is this. You have an image. You have a tomographic line, but this tomographic line, you can move it in real time. And on a monitor, you will see.
To see. Yeah, like a CT scan.
Yes.
Like where you move through the sections
you
and
will,
see
you
all
will
the
see
different
all
layers.
the things. Because
Right.
I remember when we did, but also on the Khafre project, you have you launch a process. You have to wait 15 days, and I forgot what we are watching. So it is a bit not so useful for it is for research. Okay.
So you want to be able to
We
do
did the paper, but if we want to do several scans, you have to wait a lot to have the results. So, in my personal opinion, now the thing that we are doing is this: we have to rekernel the software. We have to use a rise of GPU.
Yeah.
Maybe we can also multiply the processing power also for, I don't know, I can say 10,000 times. It means that 15 days will become 30 seconds. It's good, passing from 15 days into 30 seconds. But to do this, I need investments. We need, I can't do it. But in my personal opinion, the future of this, because here the problem and thank you for giving me raising these problems.
Yeah.
That we are having now is related to the processing time, because this is only one tomographic line. If you move in real time on a plethora of adjacent tomographic lines, you can see everything. And you do it real time, like when you go to the doctor.
Yeah.
You make a scan of your.
I don't know whether it's CT scan or MRI, but where they can literally move through the different. I think it's a CT scan. Yeah, where you can literally move through the sections in real time. But it's also, like you said, it requires super high processing power.
Yes.
And this is just the
it's
initial.
Possible to do it.
Of course, yeah.
This is 1.0. You can move also.
Right. That's what I was going to say.
But it's not for me. On my. I don't know.
I think the burning question people have now is what gives, if this is just one tomographic scan, you have to wait 16 days, is that the same method outside of the angle of incidence that you used for detecting the substructures below the Khafre Pyramid?
It's the same method.
Yeah.
It's the same method, absolutely yes, and has been improved in terms of details of the method.
Mainly angle of incidence or anything else?
We have used different incidence angle, scanning the below the earth, but it's the same.
Okay. And all the validation that you've done at Gran Sasso, Osiris, was that with the multiple angles of incidence and the triangulating?
I tell you.
Okay.
Yes, because the Gran Sasso, it is very high. It is nearly 3,000 meters, 2,990 meters, 93, I think. And there, the layover effect is massive, present on the SAR image. So I had to let's say order different images in order to choose the best one. For me, the best one. Maybe other image could be also better. In order to retrieve the laboratory, to detect the laboratory.
So here's another different scan of the King's Chamber. Yeah. So when they say Z chamber, they're referring to what's conventionally called the King's Chamber. And this scan image looks qualitatively different than what we see here.
It's not the same tomography. It's
Correct. Yeah, a different tomographic line. So you've gone in and taken a different vertical slice.
As I told you,
Yes.
if you have speed, you can do it in real time.
Right.
So you will in real time choose the best one to show to the
Right.
the
Yeah,
customers
yeah.
who wants to.
And so in my interpretation here, so you see the horizontal signatures.
This I like it.
These are the granite beams that are part of a structure known as the relieving chamber, which is a structure located above. You can see the diagram on the left. Again, this is a known archaeological diagram of the king's chamber, not a 3D model of their interpretation of the new stuff. So these overlays are just taking known diagrams, overlapping it with the tomographic data so we can see where these things correspond. And if you look there on the right, you can actually kind of see the slope angle of the triangle at the top.
Yeah.
You see it kind of, it
There
picks
is,
that up to a little bit on the right. You see that slope that aligns with the top of the chamber and the horizontal signatures of these granite lintel beams. So we do have, again, the red is indicating a very strong vibrational signature from inside of the structure. And I will say that this one is pretty good. I was when I saw this originally, I was like, oh, this is promising for detection of the king's chamber. But you also have to keep in mind, the king's chamber is made of granite. So there is a qualitative difference in the material of construction that's specifically related to the quality of the detection. So for example, the surrounding mass is all limestone, but the king's chamber is made of granite, which is maybe one of the reasons why we're getting such a good signature on this particular tomographic line.
Would you agree with that, Filippo?
Absolutely, yes. I think that we are detecting also the so-called sarcophagus, which is not a sarcophagus, that is inside the king's chamber.
Oh, yeah,
yes,
right.
that facility there.
Yes.
Okay.
Yeah.
Cool.
So the only questions I had on this one, so the big red signature at the bottom is just background interference.
But you have a
The
floor, no? Of there is a floor.
Okay, and I'll get back to that in just a second.
We have
regarding
to investigate about that.
regarding the bedrock.
Yeah.
So the conventional explanation of the bedrock foundation below the Great Pyramid is that it stops somewhere near the grotto at the base of the pyramid. But in my opinion, the bedrock mound is actually much taller than we think. And one of your other scans shows what may be the true level of the bedrock. And in my opinion, the king's chamber is sitting on top of a bedrock foundation within the pyramid, which is what,
There we are detecting something that...
right. So this is a good one. This is a promising signature. You know, there are some tracers that go outside of the limits of the known chamber, but this is pretty good. Okay, so the next one here, this is where things got really interesting for me with the first paper. So again, we're looking at the Queen's chamber. And what they have here at the bottom is a scan of the Queen's chamber in the center of the pyramid. And it has been anecdotally reported and documented from the original excavations of the Great Pyramid that there is a shaft and chamber system located below the Queen's chamber. So they excavated this. They found a pit in the Queen's chamber that was filled with rubble and dirt. They excavated down into it and they found a shaft and tunnel system and chamber system located below the Queen's chamber. It is now completely covered up and sealed with modern blocks. They covered up the hole permanently. Again, reported anecdotally and in some of the documents regarding the original excavations. And what they're showing here is actually the presence of a shaft system coming out of the bottom of the Queen's chamber.
So that's very promising.
And I proposed the same thing based on these archaeological reports in my book, that there is an extraction shaft and chamber system located below the Queen's Chamber.
Yeah.
So again, when I saw this back in 2020, this was very promising and encouraging for me because they are corroborating hidden structures that are now completely covered up, which may actually exist inside of the pyramid. So I was very excited when I saw this originally, and they did a great model, which I'll show here in just a second, that shows that complete shaft and chamber system coming out of the Queen's Chamber. So I wanted to highlight this as a very possible substantiation of something that was reported, you know, in the late 1800s, early 1900s, when they were doing the original excavations, but has now been completely covered up and ignored and dismissed as not possible. But they are showing that potentially it could exist.
Yes. And I just have to remark the fact that in this tomography, we are not observing the corridors, descending corridors.
Yes.
There are two reasons. And maybe they can be both of them. The first one is that in order to detect those corridors, we have to be very sure that the tomographic line goes to intercept those corridors. Okay? And in that case, we need speed. We need the real-time facility.
Yeah.
Okay. The second is that probably is not possible because the corridor is too small. Okay.
Okay.
But I am orientated to the first one, that the tomographic line we used is not perfectly oriented on the corridor because the corridor is very small.
Yeah. And I'll show a vertical diagram of the alignment of the chambers so that we can all take a look at that in relation to the discussion of the tomographic line. My only other point on this one is, again, the subterranean chamber that's embedded in the bedrock is not detected in this scan, which is a similar issue to what you had with the Khafre project, is that it's not able to detect this bedrock excavated chamber, which is an issue when you extrapolate scanning into the bedrock to detect structures a kilometer underground.
I tell you, a piece of corridor, it is possible to detect it because it's this.
Here, I can do it here. So basically what he's pointing at is sort of this line here. Right? But how can you differentiate from a scientific perspective between all of the background interference?
When you are dealing with light, it is very important.
Yeah, because there's a lot of background interference here.
Yes. When you are dealing with light, you have a laser. The laser travels the free space and goes to the target. You see the target very well because the light travels only the empty space and not the matter. Here, the acoustics are traveling in the matter, and matter is a mess. It's the matter that is underneath that is a mess, not the acoustics that we are using to detect the matter. Okay. I don't know if I am explaining well this.
So the composition of the bedrock itself is interfering with the register of the signal.
Yes.
Okay, that's problematic because especially if you're trying to scan into a kilometer of bedrock.
You can do it this. Here we are dealing to retrieve information of things very small. Very small chambers. Very small.
Yeah, the passage is small, going down into the subterranean chamber.
You can see them.
Yeah.
But the background is composed by other targets.
But Filippo, maybe can you address the basic point Geoffrey's making, that the composition of the bedrock is important for the veracity or accuracy of the findings that you get? And so if there's any issues with certain bedrock in these readings where granite is better than limestone, and you're trying to go through a kilometer, deep of what is it, limestone?
Bedrock, yeah, limestone
limestone
bedrock.
bedrock.
Yes,
Then how are you able to
Yes.
be so confident?
But in that case, we have detected. This is very nice.
Yeah.
In that case, we have detected things that were really predominant with respect to the bedrock, how you say, background detection. We will arrive to the, or we are.
Yeah, I have everything.
Okay.
Yeah,
So
I
in that-
we
included
arrive
I
there.
included everything to
Yes.
make sure that
Yes.
people could see all of the information.
But I think we have to do part 1 and part 2.
Yeah. You
But
may have to
I get what he's saying, which is like if you control for the background micro vibrations being created by really like these are large megastructures, and so if you're trying to find a small chamber, and then you could have issues on bedrock even if the whole thing is happening superficially. Whereas
Sure.
if you're looking at megastructures,
And this is also
the
very
bedrock-
different.
Yeah.
The process in scanning from space as compared to the vetted technology of muon scanning, which is done inside with detectors inside of the structure.
Hmm.
You have to anticipate some flexibility in the ability to detect small components that, because again, you're scanning from a satellite from space. So
Well,
there's
this is. I mean, another really interesting question is all of your cases of validation involve structures that might be below the surface of the Earth, but not this far below. Do you have validation that exists in the case of things? I mean, obviously, like it's hard to go a kilometer plus deep just generally. I think very
In
few
that
mining
case-
and excavation sites have done that. But do you have any validation
No, I have.
that's gone that deep?
I did a lot of pilot tests with companies,
Uh-huh.
and more than 100% successful. But
Really?
that's another
When you
fish,
say-
because here we are dealing with
Sure.
archaeology.
When you say pilot
Yeah.
test
Yeah,
with companies, so this is used in a commercial context.
yes, we are moving in commercial. Yes, absolutely. Yes,
Got it. Okay. And this is like mining and
mining.
okay. Then these are, I assume you have to be somewhat cheeky about this because you're under NDA or sort of thing. Okay.
I am under NDA, so I can say
But you have-
more than this.
But you have 100% success. Like no
more
one.
than 100. More.
How do you go more than 100?
They phone me every 5 minutes.
Okay. So they're really pumped
But
to
I
work
can't
with you.
say more than this.
and
I mean,
I
that's
will say
fascinating.
the mining
Yeah.
and metallurgical applications of the technology
Yeah.
are directly applicable to the specific geology. There's metal ore mineral deposits all over the Giza Plateau.
Yeah.
You're familiar? I don't know
Then
if
we
we've
speak
talked.
about this, because
I'll
this
show
is
it.
very interesting.
I'll show it in just a minute because
Yeah.
there's iron ore metal mineral deposits all over and below the Giza Plateau.
Yeah.
We have chemical analysis data from these iron veins, hydrothermal mineral deposits embedded in the bedrock that are permeated with rare earth elements. Gold, silver, things like platinum and titanium have been discovered in these metal ore veins embedded in the bedrock of the Giza Plateau.
Mm.
So there's a direct correlation between the applications that he's describing for this technology and the investigation of the truth of what's really below the Giza Plateau.
Yeah.
We may differ on our interpretation about that, but we absolutely agree that there is something down there that is absolutely important to understand.
I always
I agree
love
with you.
Yeah.
I always love when I bump up against the limits of what Filippo can say, because I do feel confidence coming from him that
Sure.
there's like a lot that isn't quite open source that,
Yeah.
both commercially and defense wise that he just can't really talk about.
Sure. Yeah. And we've talked
I'm
privately
sorry.
about that as
Yeah,
well.
no, it's okay. It's
Yeah.
okay. But yeah, again, unless you're like a great con man, which I don't think you are.
Yeah.
you know, I
And
think
my
that's, like, pretty
only
confident
questions in
inducing.
regard
Look
to
how
this
nice
is
the Queen Chamber. Look.
yes,
It's there.
but
Guardate,
but
yes.
what
Look at that corridor.
but what about-
the story of that corridor?
but
It's
what
very
about
nice.
the Grand Gallery and that's good, but we're completely missing the Grand Gallery and
Yes.
the King's Chamber.
I tell you why.
So you have 1 out of 3.
Well, let him. Okay, so what? Yeah, why do you
I
think?
tell you why. We go back into the things that I told that that we were discussing 5 minutes ago. In this tomographic line, you don't see the Grand Gallery, but the Grand Gallery is good that I don't see it, because I can see the air that is inside the Grand Gallery. It's good. The Grand Gallery is a tube like that.
Correct.
A rectangular tube. I
Yes.
see the top of the Grand Gallery, then you have the air, blue, and then I don't see nothing. I see the Queen's chamber. It's good like that. You move the tomographic line, you integrate,
Sure.
and you perform a 3D reconstruction. But
Yeah.
to do this, we need the computer, Geoffrey.
Right.
We
Right.
need a rise of GPUs that at the moment I don't have.
What's the word you're using? A rise of GPUs?
An
rise. got
array,
it.
no?
Array.
Yeah.
A mainframe like that.
Okay, an array of GPUs.
Array.
That's what I thought it was saying.
Yeah,
Okay,
okay,
got
yeah.
it.
I'm sorry, I'm Latin.
No,
No,
it's
no,
okay.
no,
It's
no,
okay.
no.
Yeah.
Okay.
Yeah. So you need more compute essentially, and you need to do this, be able to do this in real time,
If
live.
I have thousands of GPU, we can do it.
So how much, out of curiosity, how much money would that require?
I can't tell you now. I don't know. But
What if there's an investor in the audience that wants to help you out? Is there a certain amount that would help you?
maybe with I don't know, with I don't know, millions, in the order of millions. Yes,
Okay.
we can have. We will speak about the foundation that we are standing in Malta, setting up in Malta. We have rented a nice place where we have installed a solar power station, and inside there we would like to set up a data center. And there, if we have donators, we can buy a mainframe with an array of GPUs.
Well, we should, just for humanity, somebody should do this, not for profit, but
for human,
to like
the foundation works. Philanthropic.
No, it seems like money well spent if you're, you want to go kind of Carnegie Gospel of Wealth. This should be like the first on your list. So and what you're working on too.
With
by
the
the
three
way.
computers that you saw in my house, we can do this.
Yeah. So but what do you say, Geoffrey, to?
And they are also expensive,
Yeah.
those computers.
Got it. Oh, there you go. Okay, that's established. Geoffrey, what do you say to Filippo's point that the Grand Gallery is actually detected? It's just one vertical slice, and you do see the air.
Yeah, I'll get to that in just a second.
You see that the Grand Gallery is blue because you have air inside the Grand Gallery.
Yeah.
Okay. So I guess he's saying here,
the Grand Gallery is vacant inside.
Right.
Okay.
Right. So the other things I wanted to point out here. So this signature above, and this big signature
that's
here,
the big void.
The big void.
Yes, and we have detected the big void also.
Yes.
That's the big void.
And we'll get to that in a comparison between the location of the big void suggested by the Muon team and the position that has been detected by the SAR team. It's slightly different.
In my personal opinion, that is the big void.
This
because
one
it's located,
or the big one here?
The big one there.
The big one.
Yeah.
Okay, so the Muon team is saying that it's located directly above the Grand Gallery, the position of the big void, that they're actually going to be excavating into the Great Pyramid in 2026 to investigate the big void. So an actual exploration is coming up to get a chance to see what's in there.
Okay.
So again, I'm just objectively looking at these things. I do agree there's a fantastic signature here. Yeah. And we talked about this too, Filippo, at the Malta conference, that it's a different in the slice.
Yeah.
If you move the slice, you might be able to better detect it. So another thing here is tag 17 and 18.
That's fantastic in my personal opinion.
Which is
very nice.
I have it again in a slide. Okay, so let's look at the position. So here is the configuration of the Great Pyramid, and this is the vertical alignment of the chambers. So you can see, if you were to scan the tomographic line at the far left of the King's Chamber, you would only pick up the King's Chamber and not pick up any of the other stuff. if you scan on the far right of the king's chamber, you should pick up all of the components because everything would be aligned in the same tomographic slice.
Yep.
You cannot detect the king's chamber without also picking up the grand gallery, queen's chamber,
you have to do
subterranean.
multiple scans,
Correct.
no?
Correct. Yeah. There's
And so
also
why the array of GPUs.
Sure. But this is kind of an explanation for why that may be the case, is the different slices that break it down.
Could have been on the left.
You may do a slice down the middle that picks up the king's chamber and the queen's chamber here and here, but it doesn't pick up the grand gallery.
Yep.
So this is an explanation for why we get register of certain chambers with different tomographic lines, because we're just slicing down the middle. And the slice doesn't always land on all three simultaneously. Okay, so the next one here is the discovery of this new passage.
Yeah.
Right? On the northern side of the Great Pyramid. They just
This
drilled.
I have to say this. We discovered it for the first time.
So
that's amazing. Is that
yeah.
true?
So let me explain what we have here. So we have
Yeah.
tag 17 and tag 18, which is showing this little
the
passage
corridor.
here.
That's the corridor.
Yep, right
Okay.
here. And it starts right here
Yes.
under the chevrons, which is
Absolutely,
where they
yes.
found this passage. And we have an overlay of the chevrons and the new passage
Yeah.
that was discovered.
Mm.
My only issue on this
Yes.
is that the signature actually starts out here.
Yeah.
Mm.
Yeah.
You know,
Those are
this is-
multiple reflections of the radar.
So reflections of the radar.
Yes. Multiple reflection. The interaction of the electromagnetic waves from the floor of the pyramid and the pyramid can give you multiple reflections. It's normal.
Okay.
And that multiple reflections affects also the tomographic line.
Okay, so
The
you're
to- the
saying
tomographic,
reflections of the radar
Yeah.
can create signatures
It can
that
be
would
mitigated.
appear similar
Yes.
to the signature of an actual chamber.
No, can be mitigated only having multiple scans. And so you can average your results and you see them absolutely better.
Okay,
Okay.
I'm with you. Yeah, all right.
It's simple. That is the best signature you have it on the chevron, and you are detecting the chevron. Look.
Yeah,
because
here,
Why
right
am I
here.
saying you multiple
And that,
reflections?
but
Because you have the pyramid, then you have the chevron like that, and you have the other, and there you have such multipath of the radar.
are you saying that tag 18 wasn't even known by conventional?
No, it
archaeology?
was known. The
Okay.
chevrons are visible on
Tag
the
17
outside.
was not known.
Yeah,
Tag
so
We
they
knew
they
it for the first
recently
time.
And
they-
what is tag 17?
it's just
A corridor.
it's a dead end shaft. You can see the overlay of it
A
here.
corridor.
Yeah, so they
But
recently
that's remarkable that he discovered it basically through the, is that correct?
Before that,
they detected it. Yeah,
Yes.
this was detected by the team in 2020.
Okay.
And they recently went inside of this with a microscopic camera. They drilled in below the
and
chevrons
there was the
to look
the-
into this dead end. It's a dead
On
end
the
shaft
corridor.
on the northern side of the Great Pyramid.
Well, that's
And
impressive.
if you go to the result,
Yeah.
if you switch off the overlay, you can detect also the top of the corridor and the floor of the corridor. There are two lines.
Yeah, the top here
Yeah,
and the bottom here.
And
Yeah,
you can measure also.
Yeah.
And if you compare the measurements with the video, because they scan it, are the same. And then you see that is 9 meters long. I don't remember, but it's 9 meters long. There is something, a piece of stone that goes. But here you can see what there is over that piece of stone, which is, I tell you,
here.
this one. And I am waiting somebody that is discovering that anti-camera.
Anti-camera,
Yes.
anti-chamber, what?
It's a chamber. I call it anti-camera. It's
Okay.
a chamber.
Okay.
And that chamber goes directly to the Grand Gallery.
Hmm.
Okay? And then allows you, for me, also to go naturally to the big void. That is the real position of the big void, is that one.
Mm.
Okay.
Geoffrey, the future will give what
Sure.
what
Yeah.
No, you're
what
So
is
actually-
able to give.
you are
so I
you are
will say-
staking a claim. I love it.
So Matt Bell
Yeah.
from the Limitless podcast
Yeah.
is involved in financing of the development of robotics. to investigate the shafts in the Queen's chamber.
Cool.
They're going to be sending a robot up the northern shaft to drill in the comparable feature known as Gattenbrink's door, which was investigated in the southern shaft. They're going to be drilling through a new piece with a new robot on the northern side. And they're also collaborating on the investigation of the Big Void. So they will be, hopefully, it's been approved, but everything keeps getting pushed back and pushed back and pushed back and pushed back as things happen in Egypt. Supposedly on the table for 2026, that they're actually going to be drilling into and investigating the Big Void.
That's remarkable. And I think, it sounds like Filippo's making a prediction there. I do think it's amazing that Tag 17, this corridor dead end shaft, he's sort of, they made a claim there and they found it.
Yeah. So this was
cool.
2020. This was before the recent, I believe this was detected with the Muon scans.
Yes.
The Muon scanning. So the Muon group,
Yes.
the Scan Pyramids Project, is the sanctioned and approved scanning team that they have used for these projects. They really only collaborate with this Scan Pyramids team. We were just talking off camera about how much we're both enjoying this conversation.
So me,
and a lot of people
I love it.
have misinterpreted my questioning of the data as disbelief or an attempt to debunk, but that's not really the case at all. And they don't understand that we have an existing relationship. And again,
it is true that it's good that we discuss about the results.
Of course.
Because the results is not like a religion. No, it is
No.
something that we can discuss.
I love that. Yeah, first, the fact that you're saying it's not a sacred cow or third rail, it's just a thing you can talk about and, you can criticize and you can defend and, it's all good. That's a beautiful thing, that commitment to the kind of, Socratic process. But I was also, Geoffrey and I were talking, I think a lot of these discussions go into it's always framed as adversarial. It's always skeptic and debunker versus person making some bold claim, and then the skeptic doesn't even look at the assertions and make first principles arguments. It turns into this it devolves into ad hominems, and you get into these high level heuristics of probabilistically this thing can't be true or whatever. And what I love about this conversation is, and then we can get out of the meta and get back into the first principle, but it's that you are really just asking questions that I think everybody wants to know that are at the first principles level, and they're reasonable questions.
I'm captivated by this process. Again, when I found this in 2022, I was like, this is super important. Whether it's true or it's not, it's the development of new technology and an approach that could eventually be implemented into something very significant, which is the purpose of all the videos that I've made about this. Have prefaced it with saying, this is the type of technology we need. We're on the precipice of a greater understanding using unique methodology to understand the structures that's going to get us to the deeper understanding.
Yes.
And Filippo, you said during the conversation that it's still in the initial stages, and there's improvements that can be made with the technology, further investigations that need to happen.
We need hardware. We need a lot of hardware. Hardware and power.
Can I ask one thing actually before we get back into this, which is, speaking of skeptics, I did watch Flint Dibble's video about you, and I found a lot of it to be a little ridiculous. But there were certain points he made which I think were
we can discuss now. If you remember,
I do remember. I remember one point which I found very valid. Well, one of the points was like it's too hot to build that deep. It's too hot to build artificial structure. So that felt reasonable, and we can get to that.
It is connected to the heat is connected to our research project, that the third part of this research going in situ, but we will discuss at the end of this conversation.
Okay.
Sorry,
so a little teaser there. No. So let's definitely circle back on that. And then the second one, which I think relates more to this discussion we were just having around the commercial use cases
Yes.
of this technology is he said you let your patents expire. Is that true?
Yes, my initial patent at the moment is expired. Absolutely, yes. Maybe we can recover this. In the United States, we give you a grace period in order to recover this patent. Maybe we will do it. But I have submitted a second patent, which I can't disclose the things, but I have submitted a second patent that is connected to the first patent and gives huge novelty, but I can't speak about this.
Fair enough. Yeah, you definitely shouldn't.
Because it's a disclosure.
Yeah, no, don't telegraph your IP. I think the question I would have is if the first patent is in some way related to the second patent, and it might be a gateway if I'm a scientist and I figure out what's going on in the first patent, which you have telegraphed it is in the USPTO.
Yeah.
I read it. It helps me figure out the second patent. Why wouldn't you also try to maintain the first patent and just keep enforcing it?
Yes, but I tell you, Jesse, the question of patent, or in the commercial, or in the philanthropic, I want to work on the philanthropic and also in the commercial because I like to work with my technique. For me is very exciting. But yes, the patent will give you the rights to be only alone to only me give me the rights to commercialize exclusively this technique. Okay. But the important thing is also the technology that is behind the software. No, the software is crucial in this deal. So
got it.
Yes, patent, no patent, but you need the software.
Okay, yeah, and that's a good answer because you speak to most people in fields of aerospace or kind of hard science, and they'll always say patents are barely enforceable.
Yeah.
It's really about trade secrets, and it's about knowing how to do something that no one else is going to figure out. It's not really about the patent. So I appreciate you addressing that.
Is not so important. But and now we have a second patent. But the crucial point here is the technology, and the technology is made by hardware and software.
Yeah. It's funny. It's like, I don't know why would you go out and make a YouTube video and just in this shrill way start like, yelling at you instead of just be like, hey, Filippo, like, my name's Flint. Like, like, why did you let your patents expire? Because that answer, you have a reasonable response there. So I don't know. It's interesting. But Geoffrey, I think you should continue with your kind of first principles questioning.
Well, I think this is why this conversation is working because like we're friends, like we've met before and we've spent personal time together. The important thing for me, as I've shown in this presentation, is that if we do have novel structures, it's critical that they can be interpreted into a functional hypothesis. For example, the shaft system below the Queen's Chamber, it's been reported in archaeological documents, and you should have a model that interprets that into the function of the structure, which I've shown it's part of the extraction shaft system that was used to remove the product solution from the Great Pyramid. So I have done that in my work, is entertain these ideas, although speculative at this point, because we haven't done actual archaeological excavations to prove any of this yet. I've taken it and incorporated it in a hypothetical working model where these new structures actually fit with what I've proposed. For example, the big void, it's in a perfect location for a heat exchanger, right? Anytime you have exothermic reactions within a structure or an operating chemical manufacturing apparatus, you want a mechanism that can remove some of that thermal energy from the system. And the big void, although it's shown by the Muon team in a little bit different position, located above the Grand Gallery, is the ideal position for a heat exchanger that would remove some of that thermal energy from the reaction in the Grand Gallery, which we can get into much deeper depth. Whether which one comes out first, we don't know quite yet, but we'll get into much more depth on the function of the Great Pyramid and how this new void, it's definitely real. right? We've detected it with the muon scanning.
There
You've found it already,
Yes.
and they're 100% going to go in there and
Now
investigate
we are
it.
dealing which is the exact shape of the,
Right.
where it is exactly a meter
Yeah.
on the left, a meter on the right, but there is
Yeah.
a big void. It is.
So that's
I
actually
can't say
a good
it's pure,
transition. Yeah.
but it's very probable.
So, we've talked about the initial scans. Here on the left is the first of the 3D models.
Yes.
So before, what we had is an overlay of the processed focused data
Yeah.
on top of existing archaeological diagrams.
Mm.
What we have now are the new 3D models that, Filippo, can you explain how these 3D models were developed? Who made these and how were they created?
The 3D model was done by the authors of the paper. So it was done by Corrado and me.
Right.
Together.
Right. So basically what they've done is take the focused data and interpreted it into a new model
Yeah.
showing all of these features that they've discovered, which we'll
Yes.
get into that now.
Right.
So talking about the position of the big void. Okay, so again, the Scan Pyramids project and this muon scanning. So muon scanning involves cosmic ray absorption. These cosmic rays that come down from the atmosphere. There's a series of detection devices that are put inside the pyramid. You can see them here in the Queen's Chamber, and they also have some on the outside of the pyramid on the northern side. And essentially, these muon detectors detect the absorption and diffraction of these muon rays that are passing through the pyramid structure, right? So these cosmic rays actually do permeate the structure. The chambers will reflect them in different directions, and the detectors monitor the difference between the body of the pyramid and the chambers of the pyramid.
Which, by the way, I will say it's an energy matter conversion that's going on there too. And so it's similar, for the people who
Very
are like, you can't derive matter through energetic means, it's sort of,
Yeah,
somewhat analogous technique.
So in this instance, they're just using natural energetic electromagnetic energy that's coming from the atmosphere. Muons, yeah,
It's not
cosmic rays.
electromagnetic, Cosmic rays.
Right.
Not electromagnetic.
Okay. So can you clarify
But
the
it's
difference?
the same. It's the same. The principle is the same.
Right.
Is it cosmic ray, not electromagnetic?
No. Electromagnetics are photons, light.
Yeah.
Cosmic rays are particles
Like
that are very small that penetrates matter.
I think I associate cosmic rays with neutrons. Is that roughly?
And the neutron is very big.
Or cosmic radiation.
It's very big.
Okay.
It's very big. Neutron is like a bullet that it's,
Yeah.
it's very big, and it is the principle of.
So what particles would you associate with cosmic rays?
Neutrone is a big bullet, big one. That is the principal actor of the fission in nuclear energy production reaction. Okay, because the neutron goes to another atom that splits the atom of uranium. It splits and generates other three neutrons that goes to split other atoms. And so the chain reaction is activated after a so-called critical mass, okay, of uranium 235 that has been enriched at least from 25% up to 90%. It depends on the application. In the civilian application, so in civilian, so power plants, atomic power plants, not nuclear, atomic power plants are 28% of enrichment. No, for maybe less, 15% enrichment. I don't remember exactly the number. And then you can go also in 90% for other kind of application. Muons are smaller, so they penetrate the huge mass of the pyramid. But while they are traveling along a line of sight, when they find a void, the law of
Refraction, yeah.
they can change slightly the orientation of the path, like that. Tac. And so the detectors will detect a history of these muons while are traveling the pyramid. The good thing is that muons are free because they are the cosmic ray, and it is like a transmission that is parallel because they come from very far, and so they are parallel. It's a parallel transmission. So it is like a plane wave in the electromagnetics. In the term of signal processing, I can do it blind, though that signal processing is a very basic signal processing that they use. On the detectors are detecting the muons, and so you have a history of integration, because I think that they has to be there months.
Yeah, it sits there for a long time.
So you have an
correct.
integration of months. The difference between muons and my technique is it's not so different, because you have to focus the raw data there. You have to do an FFT in order to retrieve the tomographic slice that belongs between. The tomographic line is due by the detectors that are in the chamber, and what you see is a vertical curtain that starts from the detector to the end of the pyramid. That's your tomography. Only there.
Yeah.
And in 6 months, I don't know how many tomographic slices you can retrieve. It depends on the detector width that you have inside the chamber.
Yeah. So this muon technology is the accepted and utilized archaeological procedure for detecting these internal chambers. And as you can see here, they had these muon scanning devices and the detectors set up in the Queen's chamber, and they were investigating the presence of this big void.
Yeah.
And you can see here so again, to clarify the difference, the muons actually do penetrate the body of the structure, and the detectors are measuring the difference in the reflection and the absorption of the rays as they pass through the various chambers. And they only they don't show, like Filippo's work does, a two-dimensional slice. So it doesn't have the same tomographic line capability. The raw data that they show in this paper is only a top-down view, because that's the way the detectors are looking, right?
Yes.
So they're looking up.
But because they don't know how to do it. Because you can, I don't say anything now, because you can do also tomography with that. They don't know how to do it.
Okay.
Because you can do, but I don't say things that then they can replicate.
Yeah, and that's why I incorporated this, because I wanted to hear your professional interpretation and opinion on this accepted technology, and the reason why there might be a difference in what they're showing versus what you're showing, because there has to be an explanation.
That's a two-dimensional horizontal plane, not vertical plane, but it's good.
Yeah,
we can interpret it like that. But you can do also, using muons, also tomography. You can do it.
Can we get a little context on who's doing the muon scans and when?
So this has been going on. So I'm certainly no expert in this. This paper is published by they work with a Japanese team that's been sponsoring and providing the funding for all of this, working in conjunction with the Ministry of Antiquities. And I think this was published, I don't have the publishing date, but this was
But muon detection generally in the context of the Great Pyramids, or the Giza Plateau rather, would date back to like the 70s, I believe.
Yeah, so they actually
Luis Walter
so
Alvarez.
they muon scanned the Central Pyramid back in the 70s, and I have that paper in here as well, so we can discuss the muon scanning of the Central Pyramid compared to the new SAR scanning.
And
so
this
I'm not an expert in the technology.
Yeah,
that's why I would defer to Filippo to answer the questions.
You went in the detail about this paper, because you are now explaining me how we can read their data. their results.
Sure.
That is important.
Yeah, and again, I wanted to be as transparent as possible
Yeah.
in the conversation where I present all of the information that we have to analyze all of it in conjunction with what the SAR team has presented. And this is just the opposing technology that has been conventionally accepted. Because again, SAR is new, it's controversial, people are either loving it or hating it, but this is the accepted technology.
SAR Doppler tomography is, yeah.
Correct.
Yeah.
Yeah. And the muon scanning is accepted within the archaeological community as the established methodology for scanning internal chambers.
And just to add a little context, I think the original guy was Luis Walter Alvarez, who was not only extremely high up in the Manhattan Project and instrumental in, nuclear fission and creating the atom bomb, but he and his son actually developed this theory that dinosaurs were wiped off the face of the earth due to an asteroid impact, and it wasn't really accepted for a long time.
I think I want to say this paper. I'll look at the name sounds familiar,
Yeah.
and he may be the author of this because it was during the 1970s.
Yeah.
when they muon scanned the Central Pyramid.
So this was this idea that 66 million years ago, you had this, big asteroid impact, and it wasn't really respected until later on. And so I do think the muon scanning was always a little bit more accepted, but it is interesting, that things start stigmatized and then they often become
so
accepted.
This technique, you can't separate, and this is important that I have to do. It's good. I love this technique. But you can't separate vertical layers. So you are watching here the sum of all the vertical layers composing the pyramid.
The layers, vertical layers.
No, vertically, no, sorry, horizontal layer. Vertically,
Right,
the vertically sum
Yep.
of all the horizontal layers that the sensitivity, probably a cone sensitivity,
Yes.
the detectors are watching.
Correct. And they also mention this in the other paper. The cone of detection is mentioned in the paper regarding the Central Pyramid scan. So what we're looking at here is, again, it's the
Yes.
focused, processed data of the muon detection process.
Yes.
And what we have here at A,
They can detect a pseudo vertical sensitivity by using 2 or more observations. So you put a detector here.
correct. Yeah, you can
And
see
you
the
put
two.
a detector there,
Yeah.
and you perform photogrammetry in the muon domain. With photogrammetry, they can, let's say, with an approximation, twice the approximation of the position of the big void, because they are not sure, because you have a base of difference in viewing in the muon domain.
Yeah, so the view angle
The view angle.
of the muon detectors,
Yes.
you can see here that the one placed inside the Queen's chamber is looking up, and then they have the second detector on the northern face so that it's looking up in this direction and then into the structure so that they can do a comparison between what's detected on scanner A and scanner B to come up with a composite image of the location of this new void.
Mm-hmm.
So again, I thought this was important to include, and this is the data.
Absolutely.
So A is the signature on all 4 of these of the King's Chamber. B is the location of the Grand Gallery, and here is the detection of the new void. So they're showing it. Again, this is not very reassuring either.
Understand.
Yeah, exactly. Well, so,
I'm sorry, Geoffrey, but my results are better than this.
well, no, Filippo, that's why I put this in here, was for the exact reason.
We say, chiedi all'oste se il vino è buono in Roman, in Latin.
You said that during the presentation, and I still have no
What does
idea
that
what
mean?
it
È come I tell you, I will translate, but to all the Italians, è come chiede all'oste se il vino è buono. It's like asking the owner of the restaurant if his wine is good. Okay.
So that's why I
SAR Doppler tomography over muons all day, muon detection.
Yeah.
Okay.
So that's why I put this in here. It's for the layperson,
Yeah.
right, who's looking at Filippo's data and they're saying, I can't understand anything of what I'm seeing here. It just looks like a bunch of mess.
Yeah.
If you look at this looks like a bunch of mess too, right? And you really have to have an expert at that particular scanning technology do a detailed assessment of what we're actually looking at here. But the reason I put this in is this is the data that they have used to justify the archaeological excavations that will occur to investigate the big void. This is what it looks like.
Oh yeah, I mean,
it's like, what the hell are we looking at?
Nice void, big
yeah.
void.
Yeah, I mean, it's like, so when I pulled this up after I did Danny's show,
a big mess,
because
big
we were
void.
talking. Yeah, exactly.
Exactly. No, it looks like abstract. It looks like a nice album cover to me.
Yeah, because I wanted to see. I'm a stickler for looking at the raw data. I don't like looking at the models. I don't like, I want to see the actual. Show me what the scans show. Like we were talking about with the labyrinth and Hawara scan.
Yeah.
Show me the actual scan.
Well, this was. I mean, I don't want to get too
discussion.
off course, but
Exactly.
and we'll bring this up in our one-on-one. But you mentioned to me right before the podcast, I was like, what about the 40-meter long tic-tac shaped object in the labyrinth and underneath Hawara? And you were like, that was only written about in a blog post. And I, to be honest, I'm a fan of Ben Van Kerkwyk, so that was the first time I had heard. And he was kind of pouring a little cold water on your stuff as if that was less tested than the tic-tac shaped object. But
it's been
this feels more legit to me if that's from a blog post.
It's been interesting to see the reaction of the community.
Yeah.
And people because we're all in this community of alternative ancient history.
Yeah.
And the reaction of some people, again, has been complete rejection immediately. Some people love it. 100% no objections, but there's nobody that's really taking a middle ground on this and asking honest, objective questions. It's like, I'm kind of honored to be in the position to be here to have this conversation because I've invested a lot of time in trying to understand this.
Yeah.
I've read the papers. I've looked at the conventional scanning stuff. I've investigated the muon data. And this is super important to my overall work is making sure that we really understand what's going on here.
Love it.
And
let's keep going.
It's just been weird to see the reactions of people in the community where they're either debunking it or they're on board 100%.
Yeah.
And there's nobody that's really.
Well, it's just ego. Your identity gets wrapped up in a position and then you pre-crystallize knowledge. And you end up engaging in bad thinking instead of being like, oh, damn, I don't want that to be true, but just the facts seem like it's true, you know? And it's,
if I can if I can add something constructively, I may say this. If a mutual collaboration between the Khafre Pyramid project and maybe our research team will be possible, I think things will go better.
So muons plus SAR Doppler tomography.
Mass SAR Doppler tomography plus mass muon, maybe things will be better.
Sure.
No? Sure. Yeah.
Well, I think it would also be a way, because muons are more tried and true and accepted in a conventional scientific sense, that for them, that would be like, oh, this pattern matches, like what we are deriving from the muon detection. Yeah. I think where it gets tough is, trying to get a kilometer deep with the muons. I think that's,
but once, hard. Yes, that's true, because you have to go 1 kilometer deep.
Yeah, you can't do that.
Install the detector and then you see what there is.
Yeah, and for that, you need the Ministry of Culture to let you go down there and do that.
With a collaboration, not the separation, a collaboration. So, I work with you, you work with me. We share what we have, we share our knowledge and our gaps.
Love it.
Okay.
Yeah.
And so sharing knowledge and gaps, I think things will work better.
Right.
In my personal opinion.
Yeah.
So my next question here, and as we'll see in just a moment, the SAR team has detected some features that go around the King's Chamber. Filippo,
so that is the King's Chamber.
Yeah,
A.
Here A.
They say that A is the King's Chamber.
Correct.
Okay.
And as I'll show you know what I'm talking about. Yes. The features that go around the King's Chamber.
Yeah.
So why do you think that they haven't shown that when you're picking it up on your data? And I'll fast forward a little bit here. This 3D diagram.
Yes.
So here is the big void.
Yeah.
You're showing it more transverse.
Transverse, like that, yes.
They're depicting it as more longitudinal. Okay. Their scans show it north to south.
Yeah.
Yours is showing it east to west.
Yeah.
and you're detecting these features that are possibly connected into the big void
Yes.
that go around
Yes.
the king's chamber. This is the king's chamber here
No,
at the
that's
center.
the
Yeah,
king's chamber.
the top
is
of the king's
below,
chamber.
The
Yeah.
top of the king's
Correct,
chamber.
yeah.
Okay.
And then
okay. So
and then you have this feature here.
Yeah, we can also overlap the results of the muon with that.
Right, right. Yeah,
we can put it
correct.
one on.
So my question is,
Yeah.
why is nothing like that shown here when you are detecting it on your data?
I don't know why. Because they are not able to detect things. Geoffrey, in that results, I'm a scientist, so I am very used to read the mess information inside things that there I'm seeing nothing there.
Can I ask it differently?
I'm sorry, but I'm seeing nothing.
I agree. This is very difficult to read.
Can I ask it differently?
Sure.
Are there other examples of things where muon detection fell short as far as predicting a structure that we know existed? We know the structure existed. Muons fell short.
There's another comparison coming up here in just a moment of the scan results where it's not showing something that the SAR team. So again, there hasn't been much competition in the archaeological space where we're comparing these different technologies. So now we're in a unique position where there is a competitor technology to the muon scanning where we're saying, okay, this is showing this isn't showing it. Sometimes this, so there's this.
But I mean, in any archaeological or scientific context, because that would be really helpful, because if it's like muons never miss, then I'm like, okay, you got a false positive on the SAR Doppler tomography.
Yeah.
If it's like, but there are a few times where muons do miss in these other cases. I do think that's illustrated.
Yeah. And again, I would love to see some control. Well, so we have a king's chamber here, and I could move the...
Oh, that's the king's chamber.
This is the king's chamber, A. And this is the grand gallery here. And what Filippo's team is detecting is a structure that goes around the king's chamber here. But
I think, as I saw in those results, in these horizontal pictures, more pictures, which I repeat is the sum of all the horizontal layers, that I tell here publicly, the research team of Muon team, there is a method to discriminate different layers.
Right.
They are not applied.
To pull slices.
Yes.
They're just looking at the composite image.
The sum. The composite
correct.
Image. You can do it.
Okay.
They can do it.
Okay.
Maybe I can move.
Yeah. Go for it.
Go. So this is the top of the Z.
Correct.
Okay.
Yeah, so it's looking down at the top of the pyramid. Correct.
Okay. This is let's say, is the king's chamber.
Correct. A is the king's chamber in these images, yeah.
Then, this is something related to the grand gallery.
Correct. B, the arrow pointing to B is the grand gallery, correct.
On the other hand, they are detecting the queen's, the king's chamber on another view angle.
Yes.
Obviously, B, this is the grand gallery.
Yep.
Okay. So we have two different view angles. This geometry and this geometry. Very good. And also other geometries. This and also this. The important thing that I am observing that here you have two things. This and this.
Yeah, that's the new void.
Wait.
Yeah.
This and this.
Yep.
Here you have only this. Why here you have only this, and here you have this and this? Which is the difference? Because the orientation seems similar. Why? There's written on the paper.
Yes.
Why?
Yeah.
Because I tell you what is, they are confusing something.
So here are the explanations of the positioning.
Okay.
And this breaks down the whole graph. And then here on this side are sort of the...
yes, the reflectivity. Okay.
Yeah.
Can we go to the previous slide, please, Geoffrey? Okay. It can be that this is the grand gallery top roof and this is the grand gallery floor. and they are, in Italy, we say, taking cazzi per contrabbassi.
Mm.
No?
What do you mean?
No, don't say it.
Taking
No,
liberties.
don't say it. Don't
Okay.
say it. Taking things to other things. They are confusing. It is possible that this is the floor of the Grand Gallery because are parallel, same shape, and this is the roof of the Grand Gallery because it's very high, the Grand Gallery.
Sure.
Of course, yes, in my personal opinion. And look, Geoffrey, this is the Grand Gallery. This, because it has a shape, a rectangular shape, maybe, look, this or this. They have to do other measurements. This is not the Grand Gallery. This is the top roof and the bottom of the same structure. So the Grand Gallery.
Okay. So
are you saying they might have misinterpreted
Yes,
the result?
absolutely. Yes.
Interesting. That's fascinating. Well, sometimes
Why I have to build a big void parallel? They say the big void is parallel to the Grand Gallery. Why?
Yeah.
Why I have to go? I have to build an inclined, so-called big void, and we are detecting the big void where they are detecting the real big void.
So let me clarify.
Yes.
Their results are suggesting that the big void is not parallel, but it's directly above. You see this area with the positive?
Yes.
So this is where they're picking up the signature of the big void.
Interpreting the photogrammetry that they are doing.
So that's why I included this,
Yes.
is because I wanted to get your opinion on these results and compare them. Again, what he's showing on his team is an east to west transverse big void that's located more down here.
And parallel, because the floor and the roof are parallel.
Yeah.
Like that.
What the Muon team is suggesting, that the big void is here
And inclined.
directly above with the same angle as the Grand Gallery. They've basically described it as a copy of the Grand Gallery directly above it. So there's just a difference between these two things.
And we haven't verified in either
The
direction.
only way to figure it out is to go in there.
Yeah.
Which they're going to do. And we're going to see exactly what's what.
Oh, I can't wait.
Hopefully in 2026.
Because if you go in there and you figure out who's right, muon or SAR Doppler tomography, that lends a lot of credence to the substructure readings of SAR Doppler tomography if you find a positive result.
Sure.
Yeah.
Now, the thing is, the Egyptian Ministry of Antiquities believes in this so much that they are willing to do the excavations based on this data. So to me, that is staggering.
What's your take?
Because when I look at this, I have the same reaction as Filippo.
Oh, really?
Is how could you possibly say with any certainty that what you're detecting here is real? It's the same argument.
How big is the community of experts that know how to read muon?
Well, that's the whole thing too, right?
Yeah.
That's why we're having a conversation with an expert, because the community in ancient alternative history, we are not experts in radar.
My question is, when it comes to reading muon scans, that seems like a expertise or specialty. Have you read a lot of these, and are you good at that, or are there people out there that are good at that? You're just basing their misinterpretation off your result.
Yes, in this moment is the first time, thanks to Geoffrey, that explaining me how to read the data.
Okay, I got it.
So we are in front of results. Based on these results, they are doing drilling.
Should we show this to somebody who's read a lot of muon scans and be like?
So I will say that in the paper, like you guys did, they also presented all of the mathematical analysis of the data detection. But I didn't put that in here because it's way beyond any of our assessment.
It is a question of geometry. Please look. If you watch the dimension of the King's Chamber and the top of the Z, so the distance, the horizontal distance of that.
So these things should actually be connecting. This should be connected into this.
So that's an error.
Well, it also depends on, again, like he's saying, it's a composite of horizontal layers.
Right.
The only part of the Grand Gallery that connects into the King's Chamber is on the top layer.
Uh-huh.
As you go down in the structure, the integration between the King's Chamber, Antechamber, and Grand Gallery, there is no more connection between the two. So basically what Filippo is pointing at here is this signature and this signature here. And he's saying that instead of this secondary signature being reflective of a new chamber, it's actually part of the Grand Gallery.
That's the
where this is the top of the chamber and this is the lower portion of the chamber.
Yes. Okay.
Got it.
Yeah.
Okay.
So I wanted to show what the existing technology was.
Yeah.
So that the lay person can see the difference between the two, what the data looks like, and see how much of it's a difficult process to understand what is going on with any of this stuff.
This is so
if
esoteric.
you are not an expert in that particular scanning technology.
Well, we should send this to people who are good at reading muon scans. But you're saying, Geoffrey, is we know that they do get that disconnection wrong, that little point. We know for sure.
Well, again, as Filippo said, it
Yeah.
could be a byproduct, the same way with SAR technology,
Well, the
where
slicing.
it doesn't pick up all of the chambers because of the particular slice.
Right.
This may not be vertical slices, but horizontal layers
Yeah.
where they're not picking the layer where
But they're
the grand...
picking the sum, the vertical sum of all the layers.
So it should have it. If it's a sum of top to bottom,
Yes.
it should integrate all of that into one, and it should show that, because the King's Chamber connects into the antechamber, which connects into the top of the Grand Gallery. So if this is actually, and you can kind of see it here.
So why are they missing that
So
antechamber?
let me show it here. So here, they actually do kind of show, you could see what would be the antechamber here,
Yeah.
the King's
That's the Grand
Chamber here,
Gallery, no?
and this is the Grand Gallery.
Okay.
This would be the antechamber, and this is the King's Chamber. And that's accurate to the configuration. So in this one, they actually do show...
Where is the big void there?
So this doesn't show necessarily the big void. To me, it's not visible in this image.
But
This is the mathematical
to-
detection of it here
it is
on the
possible
right.
to read results of the analysis of scintillation. It is another scintillation.
So this explanation
Would
down
you
at the
try?
bottom gets way deep into the technical weeds where it would take an in-depth discussion with an expert
Yeah.
to understand what's...
Simulated data. No, those are simulated data. Simulated data.
Simulated data.
No, simulated data
Similar
It's
data.
not real. It's a simulation that. Simulated data.
So you're saying this is a simulation. So it says
It's
simulation
not real that.
corrected image.
See, it's not real. The real one is we have
This
only
one.
that.
Right.
Yeah.
So is there a process, like you said with your data, of focusing? So is that what they're doing here? Is focusing and correcting the image?
That's a
For
simulation. Our numbers are synthetic numbers, are not real measurements.
Okay.
So it's not real.
Okay.
It's just to show the processing that are doing. It's not real data.
Okay. And again, I only picked the data images for this presentation because I just wanted to compare and contrast the raw data from your team
Okay.
in comparison to the raw data from the Muon team. Who knows which one of these is right? And again, we're having a conversation with an expert on SAR technology. The next person we should have in this round table is an expert on Muon technology so that we could all understand exactly what's
Friendly,
going on
not
here.
like
Oh, of course.
friendly. If
Yeah.
he was today now here, maybe we could explain one to each other
Yeah.
our results.
No, it'd be
But
so
friendly.
helpful.
And I do have the whole
yeah.
paper, but I would have
Yeah.
to close this, and then it would be a huge tangent for us to look at the math presented in the
let's
paper.
not do that.
So there's a
Yeah.
whole paper about this. If anybody wants to do a deep dive into Muon technology, they wrote a deep paper, the same as with your first paper, that includes all the mathematics
So the
in the scan processing.
TLDR here is that you have
exactly.
some
Exactly.
in some, definitely tried and true method, muon detection in many cases. And then at least in the case of that one kind of cul-de-sac shaft, we, tried and true as well.
So my only point with this is,
Yeah.
from the perspective of the Egyptian Ministry of Antiquities, which is the sanctioned body for investigating the structures, they used this to find the shaft that we just saw, that your team also found. And they're using this data to justify the excavations into the big void. So this is one of the first times that they're going to do a major excavation into the Great Pyramid. So there's only been a few other instances where they've actually drilled into the structure. So that's a major project to be approved by the Ministry of Antiquities. They don't do that lightly, right? It's a big decision when they decide to excavate into the structure. So they do believe in this enough for them to justify this project. But again, who can make sense of what's what on either one of these things? You really have to have an expert, a la Filippo here, or an expert on the muon technology to really explain exactly what's going on.
Yep.
So next, I really want to get to because again, this could turn into a 6-hour-long discussion, and we'll be here for the rest of the night.
Now we move it fast here.
Yeah. So I can skip through this. The reason I wanted to show this section of the paper is because the SAR team is finding other structures, like tag 1 here on the right is the data shown in tag 1 here in the model. So this feature here that goes down into the bedrock, then there's this step-like feature here.
Probably.
Again, so they're interpreting this data over here on the right into a model to show their interpretation of what this signature actually is.
Yep.
So that's all I'm trying to show here, is the presentation and the development of the model itself.
Yep.
So you'll see these different tags, tag 1, tag 7, and tag 4. Tag 7 is this transverse east to west beam-like feature. And then you have these step-like features here. I actually proposed in my video a while back in 2021. So there have been researchers that have proposed that there was a system of locks, hydraulic locks, that were used to move blocks up into the pyramids. So an interesting interpretation for some of these features could be construction-related features that are still encased in the body of the pyramid that are remnants of the construction process, like water locks, where they were using water locks to float these stones on rafts up into the pyramid body. So again, it's important for any researcher who's analyzing these things to be able to have an interpretation of the function. That's kind of my job in this investigation, is when I see stuff like this, I either have to assess it from the perspective of the operation of the structure or possible vestiges of the construction process. And it would make sense even if it was like the internal ramp, for example. You would have remnants of that internal ramp inside of the structure. If it was water locks, you would also have remnants of the vestiges of the water lock system encased in the final structure. So this is just showing some of the things that the SAR team discovered inside of the Great Pyramid that are new, undiscovered features.
Okay.
So we have data on the right and model on the left.
Okay.
Again, this is just going through showing these linear features here and the different tags that are represented in the model here. So tag number 2 is the feature on the other side. So you have 1 here and then 2 over here.
Okay.
Same thing with...
this you see it very well.
Yeah, here we go into some more where...
there, the Grand Gallery, you see it.
Here, yeah. So I was going to point that out here. So this is the Grand Gallery.
And you see also the superior part of the Grand Gallery. That... you go up. There are features that are connected to the King's chamber. No?
The antechamber. The antechamber here.
This is very clear. You see it.
Yeah. So again, I'm just showing to everybody who hasn't seen this yet, the raw data on the right and the extrapolation of the raw data into the 3D model.
Yeah.
So they're just interpreting the features that they see here
Did-
into this model.
Can I ask you a question?
Yes.
Do any of these structures that they're interpreting from the raw data fly in the face of what conventional archaeology would think exists inside the pyramids?
All of it.
All of it.
All of it.
Okay.
All of this is the only known vetted chambers of the Great Pyramid: King's Chamber, Queen's Chamber, Grand Gallery, and Subterranean Chamber. You have 4 chambers connected by a system of shafts.
We're obviously going to get way deeper into your theory in our solo episode.
Sure.
But does any of this comport with the functionality that you think the pyramid
I've integrated
has?
all of this into a functional hypothesis. So I have, Filippo, I've entertained all of these speculative features in a model of my hypothesis for how the structure works.
Okay.
For example, the heat exchanger system that goes around the King's Chamber and above the Grand Gallery, the extraction shaft connected into the Queen's Chamber, which is that shaft leading out of it. And I also have a hypothesis for how these, again, I have a number of different interpretations for what these vertical features below the pyramids might be. I've not publicly yet, but I do have an interpretation on what those could be. Reason I haven't come out publicly yet is because I think there's still more investigation that needs to be done to verify the configuration of the structure.
Yeah.
So again,
yeah.
we have more.
Yes, it is a bit confusing.
It's very confusing.
Some of the basic confusion around the pyramids, it's perennial debate and question is how they were built.
Sure.
And you have people like, I think, Jean-Pierre Houdin in France who say that there's something about like, internally, like the blocks get pulled up or something. Could any of these structures deal with how the pyramid was constructed?
Well, that's what I was saying is that so
it's like a pulley or something.
For example, in the model, these could be remnants or vestiges of a waterlock system that were used to move blocks up into the pyramid.
Interesting.
It certainly could be. My only issue with this is the extrapolation from the data into the model.
Yeah, sure.
That is things that we discussed previously. Those are 2 tomographic lines. No, if we had the chance to see the video belonging to tomographic lines, things could be perfect because you are watching something dynamically and you recognize very well the structures.
So, for example, in this one on the top right, there's so much going on with this over here.
A lot of false alarm, yes.
False alarms.
I'm aware that there you have false alarm, but it is only one. You have others.
Right.
Okay.
Yeah. So you agree that in all of this raw data, it's very difficult to say with any certainty, based on all of the interference and background data, that the model itself, so the data is clearly picking up something. It's difficult for me to be on board with the model, given what I can see and hear.
What would you say to that, Filippo? Is the level of intricacy, given the fact, you want to go back one slide?
Yeah.
Given like how in detail and intricate the model is, the 3D model that you guys have derived, and then also given what you just said, which is there's a lot of noise in the raw reading. Do you really think you can stand behind that 3D model?
Yes, absolutely, yes.
Why is it?
100%.
Wow.
Because we have interpreted really a lot of results.
Okay.
All on a table.
So
me and Corrado.
So you're basically saying you're like a pro at removing the noise? Like what's noise, you can delineate the noise? Because you said there's a lot of noise here.
There is a so-called vertical strip noise, and we have removed it now in the new tomography. So that kind of noise. So there is not any more present.
Well, then to me, it's like the Muon scans where I'm like, I don't know.
Yeah, you could be either one, right? You could be looking at both of them.
Yeah.
And I think Filippo's point about a synergy between the 2 technologies where they're merging the 2 techniques is probably the best course of action for really getting closer to the truth.
Yes, because you are detecting things and then you use another method, a complete other method to try and detect the same thing.
Yeah.
So for example, Filippo, you said that the scan happens once and it's 15 seconds. And inside of the structure,
Yeah.
there are going to be micro vibrations that are happening just based on the geology and the seismic movements or anything.
Yeah.
So is it possible that some of these detections of micro movements are simply the nature of the structure itself, where it's going to pick up something inside of the structure that's producing these micro movements?
Mhm.
Yeah.
Yeah.
So these images aren't necessarily even background noise, but it
But
could
only-
be just foundational elements of the pyramid with tiny little shifts of the block or the slight movement of the earth producing these micro vibrations that are producing a signature that's picked up on the surface. So it's the difficult thing, and this is his job because he's the expert, is differentiating between background noise, normal vibrations within the structure, and actual chambers. So that's critical in really understanding this data, is the differentiation between each and trying to separate out which is which.
But you feel confident in your ability to
Absolutely, yes.
differentiate.
I have to say this also. Everything we put, we insert in the 3D model, we analyzed a lot of results. So we are, I can't say sure, but very confident that probably things that we insert in the 3D model are the reality, are effective there.
Okay. So let's go to the final 3D model,
Yeah.
which we have. So this is another good one.
No, look how nice it is.
So again, this is the Queen's chamber here, and we have the shaft
Look, the
going
Grand
out of the
Gallery.
Queen's chamber.
Look that
Yeah,
you can see everything
the red
there.
signature here.
And also below there is something.
Here.
Yes.
Or
there.
here.
Yeah.
So again, he's the expert in interpreting what the actual data is showing. And this is the model that they've created from this perspective.
Can I just say that the 3D model looks absolutely wild? Like it looks like an advanced contraption. It does not look like something that we would normally associate with being built.
Well, it's a nice tomb.
4,000 years ago, let alone 10,000 years ago.
Yeah.
It's crazy.
So the model is wild.
Wild.
Yeah.
And my only caveat to the model is I don't see how you get to the model from the data.
Yeah.
But it's your job as the creator of the software and the developer of the project to take the raw data and turn it into something that the people can understand. Because
not only one result, with a plethora.
Can I ask you a question? When you measured the Gran Sasso laboratory, go back to that other image. Are you getting that level of granularity with it? Are you getting
let's jump to
the
that.
Instruments and all that stuff? When you see the Gran Sasso laboratory, are you getting that level of, when I say granularity, that level of specificity?
I tell you, yes.
Really?
Yes.
So I want to show you, and this is an important part of the conversation, the proof of concept. So it's nice, but we also have tons of mess. This
But
all
you
in
know
here.
why? Because I have to integrate also in the vertical dimension of this tomogram. If I integrate like that,
yes,
I will have absolutely less false alarms. But they are not false alarms; they are true alarms, because the soil, the ground, it is a mess. So the result is the reality. Okay, so why? Because the sound does not propagate into the free space, but it is propagating inside the matter, and the matter is complicated. So look, you have that mess there. I don't know if I
No, I understand. But again, from a person who, my entire body of work, and anybody who's interested in the function of the Egyptian pyramids, if there is a new novel approach to detecting internal chambers, we want to see consistency of the detection of the known structures which in here we do have a great signature
Yeah.
down here.
Yes.
Mm-hmm.
The Queen's Chamber in this one doesn't have a great signature.
Okay.
We have background data here.
Yes,
That's
that's a problem of the layover of the radar. Yes,
Yeah,
that's a problem. Of the
It's obscuring the view of any signature from the King's Chamber or
See,
the Grand
yes.
Gallery.
But I guess, Filippo, would you know that that's a problem from the layover
Yeah.
of the technique? Would you know that if you didn't know the structure? Would you be able to say,
See, that's the layover. Yes.
really?
Yeah.
You say that the pattern matches,
Yes,
that's
I know
obviously...
very well the data.
Okay.
You know.
Yeah, fair enough.
If I
And
do
then-
a report, that's the layover, and then those are real structures.
And then the Queen's Chamber, like in other cases...
You don't have only one, but you have a plethora of results. So
and
you are able to track it.
For
To
sure.
track into the tomographic dimension the different targets.
And you're
Okay.
sure you just missed the Queen's Chamber because it was too small?
Yes.
Okay. And you've missed...
It is small, but in that particular slice, you don't have it. Because you maybe, I don't remember now this case, but because we did a lot of
Okay.
study, I don't remember the case, but probably we did not align the
Mhm.
tomographic slice on the
Got it.
on the quiz chamber. Okay. And so that's good.
Yeah.
And again, what I found really compelling about this one is the signature of this tag here
Ah, yes.
going down from
That's
the Queen's Chamber
yeah.
down here into tag 15, which is represented by this blue line here.
Yeah, that is interesting. Huh?
So this has
I-
again been reported in the archaeological excavation that
wild.
there is something like this below the Queen's Chamber.
And did you
And
know...
it's covered up now.
Filippo, did you have any context on that in the historical record before you made this measurement? That's really crazy. That's pretty cool.
So that again, I have some.
No, I am listening to this
Yeah.
that story.
So
I don't
there's
know.
there's some
It's
there's
the
some
first time.
positive
Wow.
there's some positive things about it,
Yeah.
and there's also some questions and some negatives where we don't get a conclusive answer.
Sure.
So my objective with this is try to parse through what we can see and what we can't see to try to make a conclusive determination about what structures are actually there. And this is an instance where the anecdotal archaeological reports substantiate the idea of there being a shaft and chamber system below the Queen's Chamber,
Yeah.
which is certainly looks like there is something coming down from the Queen's Chamber here. So this is, again, when I initially looked at this paper 4 or 5 years ago, this was the part that I found most compelling, the shaft system below the Queen's Chamber. So now I think we can move on. This was another interesting one, Filippo.
This is interesting.
Yeah.
Look.
So we were talking about this here.
It's layover, and I know this.
Right.
layover.
So this
It's
large,
Don't care about that.
so you don't, well, let me ask a question real quick.
This is the Z. Look how nice it is.
Sure.
This is the Z. Look, and this is the Grand Gallery.
Yeah.
This I like it a lot. I like a lot this thing here. This is the Z. It is very clear. Look how nice it is. These are not simulated data, are real data. This is the Grand Gallery, and probably we are detecting, I don't know if we are detecting also the big void, but somewhere here has to be. But maybe in this tomographic line we don't see it, but we see very, very nicely the Grand Gallery, that is this, and the Z, and also the square structure that is surrounding the Z, which is this. Look, Geoffrey. This.
Yeah.
This
There's
one
there's
here,
the
look.
slide of that in the next one.
This
Yeah.
And the Grand Gallery is here, like that. We should see also the big void, but I have to retrieve the original tomography, the high resolution. But here we are not seeing the big void.
So you have it labeled there at tag 19.
Yeah.
So in this one,
Big void. Yes.
yeah,
yes.
you
I'm
have
sorry.
it. You have
It's
it
there.
labeled over
Yes,
here.
yes. I'm sorry. Thank you, Geoffrey.
Yeah,
Thank
yeah.
you for this. This help.
So
Are my results, but I did it 6 years ago, no, so I don't remember exactly how we managed to.
so my question about this one
Yes.
was this signature down
No,
here.
it's the layover.
You don't think
No,
you-
the layover is something related to synthetic aperture radar. So it's my job.
but
Okay.
Do you think, so we know that the pyramid
Yeah.
is built on a mound of bedrock.
No, that's no.
Could
no,
this
no.
possibly be
No,
a signature of the bedrock?
No, that's the signature of the layover.
Okay.
So it is something that the radar returns is so strong that you retrieve that signature also in the vibrations. Okay. It is something that I can explain it to you scientifically, if you want. But
No,
need
no,
a
I just-
pen.
I just-
I need something. To
There
write
wasn't
down.
any explanation for what this was in the paper.
It
So I
is,
wanted to ask
an
you.
aberration due by layover is well known to me.
Okay.
Okay, but inside the aberration, inside things, you can see very clear the Grand Gallery, the Z and other facilities, and also the big void, tag 19.
Here.
Yeah, okay. That's a panoramic view of what we are dealing. Look there.
We just need, I think, you, Filippo, to create known standard conventions for what is layover noise and what is, empty space and what is, physical material of XYZ density.
Yeah.
I think all of that needs to be laid out in some sort of taxonomy by you
Yes.
so that the open scientific community can kind of corroborate and check your work.
Yes. But I thank Geoffrey that invite, and you also, Jesse and Geoffrey, you invite me here, and we are, and I am giving you additional explanation of our technique. Okay.
Yeah,
So
absolutely.
today we spoke about the incidence angle, how to see deeper, how to see only the pyramid, the layover. No, that's because of the layover. Okay. It's a false alarm, but we know it. It's there. Okay. We don't consider it.
Yeah.
Because we are radar experts. Okay. It's not.
Would an average radar expert be able to tell between layover and,
An average radar
bedrock?
expert, yes, can distinguish the layover and the forest shortening and the shadowing that are the three main issues of
So they-
synthetic aperture radar. But in the Doppler tomography domain, you have to connect these things and so read
Got it.
these problems.
So you have
also
to
in-
create new conventions for kind of digesting this stuff and
Yes.
processing
See.
it.
So I just wanted to show these last diagrams, the
Yeah,
final
this is
diagrams.
the top view.
So the top view of the big void
Yeah.
connected into this square structure around the king's chamber.
I suggest you to grab this image and overlap this image on the Muon scanning results.
Yeah.
Do it. And then let me know. You will see also the big void like that.
Interesting. So again, the comparison of what we were looking at is that they're showing it's a north to south orientation.
Yeah.
Here he's showing it as a more of an east to west orientation
Yep.
connected into these other structures around the king's chamber.
Okay.
Then we have kind of the final
Ecco,
schematic
Very good. Look, you
with
see
measurements.
with measures.
So they took
Now you are understand.
So what they did here is they took the data and they measured all of the data
Yeah.
and they interpreted the specific measurements of the signatures that were received by the radar, and they incorporated the measurements and all of the unique features into a complete model that incorporates all of the new features. So we have the big void here. We have this chamber system and shaft system that goes around the king's chamber here. We have this shaft system below the queen's chamber and a possible connection point, as Filippo mentioned, between the newly discovered feature on the northern face that connects into the Grand Gallery.
Yes.
So this is a complete reconstruction, including measurements that were taken from the raw data and put into the model.
Yes.
So now let's go
Okay.
to the new paper.
The new paper.
The new paper. We established a foundation of the first paper.
Yes.
And I think have done probably an overly in-depth analysis.
Oh, yeah.
But I think it's important that we have the discussion. So there's one main question I have about the new paper.
Yes.
At this point, everybody's already, I'm going to assume,
In Malta,
everyone's
we
already
discussed.
seen
Yeah.
the raw data images. So this is the scanning
Yeah.
of the Khafre Pyramid, the
Yeah.
central pyramid.
Yeah.
And this is the data that they are showing of potential new structures located above the existing chambers
Yeah.
inside of the central pyramid.
Yes.
And I'll show you a diagram here in a moment that compares the known chambers to what we have here. And this is their reconstruction of these vertical pillars. I know everybody's seen that at this point.
Yeah.
So let's get to the proof of concepts that were presented during the Malta conference.
Yeah.
So these were scans of modern structures that are intended as proof of concept
Yeah.
that this technology can read the microvibration surface signatures
Yes.
of internal structures.
Yes. In terms of signal processing, information you penetrate.
So my main question, so here we have the Carlin Tunnel, and this is the scan.
The scan, look.
Okay, so
That is the
Filippo,
tunnel.
can you explain,
Yeah.
so the qualitative image here,
Mm-hmm.
same thing with the Gran Sasso.
Yeah.
This is the processed data showing
See.
the tunnel
Yeah.
here.
These are all the scanning.
And this is the Gran Sasso, the physics laboratory. So
look.
here we have the configuration of the laboratory.
Yeah.
And here on the left
Yeah.
is the
Real
data.
measurement, data.
Yeah.
Real, not simulated, real.
Right. Okay.
Okay.
Can you explain why this
Yes.
looks completely different from this?
Yes.
What is the difference between what is going on here in the proof of
It is a
concepts?
signal processing procedure. There we are dealing with something let's call wide area. The Gran Sasso is big.
Wide array.
Yeah. And the focusing procedure of the phonons are different. So we use something different that we can see very wide. I can say you the details, but the details are that there the focusing process is done to see, okay, I want to see wider. Okay, focus wider. And there we are observing the Gran Sasso because it's big, the Gran Sasso.
Okay.
It's big.
So what is the footprint again?
Yes.
So we said that when you were scanning the pyramids,
Yeah.
you have a 5K by 5 kilometer footprint
Yes.
area of the scan.
The footprint
Yeah.
of potential tomographic lines. But
Okay.
if you want to scan
When you
the
did,
Khafre, the tomographic line, you put it on the Khafre.
sure.
Okay.
When you scanned the Gran Sasso,
Yeah.
is it the same 5 kilometer
Sì, the
by
same,
5
the same,
kilometer?
The same.
So it's the same footprint.
Yes. Yes.
If the focusing technique
Yeah.
for this scan
Yeah.
produced this quality of an image,
Yes.
why are we using this
Yeah.
to image inside of the pyramid? Can you explain the
Well,
technical reason
Yes.
why? Because I thought these were
not
Please,
inside the
give
pyramid,
me-
under the pyramid.
well, both,
Okay.
right? So this is a scan of what's inside of the
Sure.
pyramid.
Yeah,
Yeah.
got you.
And this is a completely different type of signature
Mhm.
than what is shown here.
It's a good question.
Yes, because this
So there's a
is,
very big difference between these two things.
Yep.
So can you explain what the difference is between the process
yes.
and the
first
end
thing,
result?
The first thing is that this is black and white. Look. And the other one is another kind of colors. You see red and blue. Red and blue. So
Okay.
it is a different representation.
So again, we have here
This is
the
blue,
tunnel.
Look, blue, white.
Blue and
white,
white.
blue. Okay?
Okay.
And there you see is red and blue. In the case of the Gran Sasso, I used a different processing technique. It was like an experiment. Why here I am seeing it in a different color? Because here I attempt to do different a process of different tomographic lines, like that, because I wanted to mitigate the noise in the vertical direction of the tomographic line, like that. So to average pixel by pixel the noise, and we see that the results are very good.
Yes.
But I spent at least 2 months of processing time.
Okay.
Why didn't you do the same thing?
That's why it's not something that you can do it every day. Because I went to my friend and said, can I use your computers? Okay, yes, but I can't use his computer forever, no?
But it sounds like that's a superior technique.
Yeah.
So why
It's a
wouldn't
superior technique, yes.
So why wouldn't you use that on the most important
Because
finding?
I didn't have the computers. I am poor.
Oh no.
Well,
let's get you the computer.
Instruments. I have my instruments. I have.
But you have to understand how
You-
to like random person in the audience, they're thinking like, Filippo, why don't you use your friend's computer?
Yeah, because
With the better processing.
so for example,
Yeah.
this proof of concept
Yeah.
also wasn't presented in conjunction with the original paper either. So this is new from the Malta conference, which
Yeah.
was in 2024.
Yes.
This proof of concept is newer compared to their original scans in 2020. So to me, this is far more convincing than anything that we've seen
Yes.
thus far with the
Yes, because
original
there is-
scans.
There is the laboratory.
How much would it cost you to do the equivalent of this, but for the Khafre Pyramid substructure?
My project in the future is to do it real time, Jesse. I want to do it real time.
So how much would that cost you?
I don't know. A lot.
Okay.
But I can't say you. I don't know.
But yeah, but
Millions. Let's say millions.
how much of the validation? I do think it's important because you're saying that the processing was slightly different
Yeah.
here versus. So when you're citing this as validation, how many of the other examples, like the Osiris shaft or other things, did you use this kind of more rapid thinly sliced technique?
Everything that you are
I have all
watching,
of them.
black and white.
Yeah, I have all of them.
Okay.
Right. So
Yes.
so again, from my perspective,
Yeah.
somebody who is super focused on discovering the true configuration of these structures,
Yeah.
why would we even publish the initial results if the capability existed to do something superior that could eliminate all of the background noise and confusion? So in your first paper, you made the statement, transparent like a crystal.
But yes.
Those images from the first paper are not transparent like
Why?
a crystal.
I don't agree.
This
That
is-
this
this is transparent like a crystal. So why would we not use this is good? This is really good. This is way better, Filippo.
Yes, I know.
And that's why this is like
I know.
super important. When I was watching this in Malta, I didn't want to get into too in-depth of a conference. But when I was looking at this, I was like, this is actually something that very much resonates with me as being a very powerful technology. What you showed in the first paper, the differentiation between background noise
We
and
just,
layover and
in the
everything
first
is,
paper, the word says the first paper.
yeah,
It was the initial of our research. So
sure.
go back in time, 6 or 7, we began 2 years before the paper. So
Right.
in 2018, nearly 10 years now, 8 years they are. So the software was the initial software.
Right.
Things we did, it resonates like a crystal because it is transparent with noise.
When was the last?
Okay,
When was,
an old crystal, let's say.
Okay,
It's
sure.
like an old crystal.
Yeah, well,
What?
it's not a crystal, it's limestone, right?
Limestone.
Yeah, so limestone is not a crystal, but
No,
this,
but,
the qualitative processed image of this is very much
yes, this
transparent like
this,
a
yes.
crystal.
Yes, this
I thought this was spectacular.
yes.
And when you're presenting this data to an academic community
Mhm.
that is going to be extremely rigorously trying to tear this apart,
Sì.
the background noise, the layover, the inability to detect certain structures because of the tomographic line, I would scrap all of that and go with this.
No, this is very nice. I like it.
Well,
Because it,
let's get. I mean, seriously. I mean, this is going to drive me insane. Let's,
See, this is why I wanted to show you this.
Well, let's get you crowdfunded the money so that you can get this level of quality on the actual Khafre
but
Pyramid
also better,
substructure.
but also better.
What's that?
Also,
Oh, let's get you
also
better.
better.
Let's get you
Also
better. But even this would be, because I do think there's an issue if you're like, all of the validation looks like that, and then your reading on the Khafre Pyramid looks like the way you said. And then it's like we're basically taking your word for it. Not all my soft signaling is like you're legit, but like that's me. I'm one person, and like I also would love for there to be like an energy grid under the pyramid. So I think we need this level on the actual Khafre Pyramid.
And we
So-
will. It will be done. It will be done.
Okay, amazing. Soon.
Now, if we work in the right procedure, we will establish a foundation, and in Malta, there we will install the computers, and maybe we will do something better, also better than this.
And hopefully today I wanted to give you some feedback as a friend for ways that you can improve the presentation to the academic community, because the questions that I have are the reasons that they have immediately rejected all of the data, because there's a lot of questions. But if you lead with this, there can be less objections to the data. This I thought was spectacular. When I saw this in Malta, this really caught my attention, and it bothered me that you went from this, which is transparent like a crystal. I think this is fantastic. The scan of this structure here, you can even see it here from far away. You can see the the transverse tunnel, you can see the mountain, and you can see the inside of the laboratory.
I like
Filippo, I love this. This is the best proof of concept that you have access to a technology that can scan inside structures. But then you go from this to this. And I was like, what is going on here? There's such a huge difference between quality A and quality B that it takes away from the credibility of this, and it's not an efficient proof of concept.
Yes, but, I know, I agree with your on what you are saying, but they are results. We can't say that are bad results.
So I would
Yeah,
love to
results.
see.
Yeah.
Do it with the new thing.
Because
I would love to see
the
that.
new thing is so easy to read for a layperson that I do think it would just help your cause. And I'll defend you here and say the fact that unless you are fabricating that first image, if you're using Doppler tomography, to Geoffrey's point, to reconstruct the Grand Sasso Laboratory in that image that we saw on the left.
Yeah, here.
That is a total proof of concept for the actual technique. That's amazing.
Nice.
But that's my point.
And then you need to do that for the thing that's going viral that everybody cares about.
Watching this,
So this was very good, and that's why I wanted to show this, and that's why.
And you see also the facilities.
Here, yeah, we can see the facility here, the triangular, and this is where the interferometer is.
The interferometer is fantastic. Yes.
Okay,
the
so another
interferometer is fantastic.
Another caveat on testing modern structures as proof of concept. These are operating systems. There's electricity. There's moving components. There's people. They didn't turn the lab off for him to scan this. So there are inherent vibrations in a modern operating facility that are producing more readily readable signatures.
Ventilators.
In an ancient structure, there are no moving parts. The Great Pyramid is chambers. That's it. There's no ventilators. There's no electricity. There's no moving parts.
No.
So my only issue with the proof of concept using modern facilities is there are actual active vibrations, mechanical vibrations within the structure that are producing more intense signatures.
Yes, but you have
than
1.4 kilometers
that's
on the top.
Right. The height of the mountain is way bigger than a pyramid.
That's a fair point. And I do think that should be addressed. I think it's at the margins compared to the larger point, which is that this technique looks fundamentally different. And I think, Filippo, you should definitely do the structures underneath the Khafre Pyramid, but with this technique that you're showing here. And it's really important for these, you're giving fodder to the skeptics, if you if you don't do this. I
So,
think we need
so
to
we
do it.
always say when you present something new, put your best foot forward because it helps to eliminate objections.
Yeah.
But I can see your pride in this,
Yes.
and I felt the same way about it. I was like, okay, this is cool. When I saw this, I was like, he's really possibly on to something.
For
But
sure.
but then we again moved on to the rest of the presentation where
Yeah.
he's showing the new scans of the Khafre Pyramid. So here's another one that's another proof of concept of the Mosul Dam. And there are some turbines, 2 different types of turbines. There's a Kaplan turbine and another circular turbine like this.
Yep.
So this was another proof of concept where they scanned the Mosul Dam.
But that's using the like raw data that looks like the raw data
The secondary,
from
the
Khafre
inferior
Pyramid.
technology.
Yeah. Which I think that's a good proof of concept then.
Yes, but I have to criticize this
Okay.
in the context of ancient megalithics. In this case, the turbines are in movement and they produce
That was going to be my point, is that these are
of energy in terms
mechanical
of
moving
vibration.
parts.
Mm.
So of course there's going to
It
be
is a proof of
yeah.
concept, yes,
Yeah.
but it is a proof of concept not applicable in megalithics, because there in megalithics you need a lot of precision, a lot of sensibility.
And when you
Yes.
what's the word you're using?
Megalithic structures, right?
Megalithic.
Because
Got it.
these are operating, moving
operating.
mechanical
Just it is a
components.
rough,
Yeah,
The dam is
proof
working,
for sure.
right? So he's
But-
scanning a
And I am
piece of
criticizing
machinery.
myself.
You are,
Yeah,
but
well, it's okay. Yeah,
to play devil's advocate, if you go one slide back, like go one again, like that looks like decent. I can't read, Sardop or
It's-
Tomographic.
yeah. So this is
but
so this is the
horizontal to
go one
configuration.
slide to the right, like that.
Yep.
That looks like decent to me. That looks like it.
So let me show here what. So this is the configuration of the Kaplan turbine,
Mm-hmm.
and then this is the configuration of the spiral turbine.
Okay.
And what we have here is the
Kaplan
Kaplan
and spiral.
turbine, and this is the Francis spiral
Francis.
turbine.
So
Okay.
it's
So my only question that would help validate this is, do you have an engineering blueprint of the Mosul Dam that shows that there are these 2 different
they
types
are
of turbines?
confidential. They are confidential. No,
So you're
it's not possible to retrieve the.
that was my question, is like,
no.
this is great, and you're showing 2 different types of turbines right next to each other.
But it's sufficient to say that there's a Francis and a Kaplan. It's sufficient, Geoffrey. You can't have the effective design of the turbine chamber. You say the turbine area,
Sure,
because
that's a valid
it's
point.
very, very difficult to have it.
Sure.
Okay.
But that was just my question is, do you have access to an engineering blueprint that can corroborate this configuration within the dam? That would just
I don't know.
um,
I don't have it.
enhance. Yeah, no, it's okay. Yeah, I
I-
was just curious if you did, because that would be even more evidence
yes.
to show here is just like we did with the diagrams of the Great Pyramid.
Yeah.
You could take the
But we are
engineering blueprint.
speaking on something very simple to obtain,
Yeah.
because they are mechanically moving, and
Right.
and also the thickness is very low.
In the dam.
In the dam, yes,
Yeah.
is not.
Yeah.
I think 300 meters, something like that, is very.
So the
very-
3 of us immediately latched onto my entire point of that discussion, is that there's qualitatively vastly superior technology being used for the proof of concepts. The proof of concepts are modern mechanically operating structures that are very different to imaging megalithic structures where there are no moving mechanical points. So again, I was just, when I saw
But
this,
can I
during-
say
yeah,
it slightly differently? Which is,
Yeah.
I don't know that it's qualitative. It looks qualitatively better. The problem is, in Filippo's head, it might actually not be qualitatively better. It just looks it's qualitatively more digestible, translatable, comprehensible to any average person, because you get like a better image for a layman to read. For all I know, if I'm inside his head, he's thinking, I am just as confident looking at those like what look like thermal
Sure,
imaging blotches.
So this is the final proof of concept, the
Mhm.
Goddard Tunnel, another tunnel Again, this is the tunnel. This is the mountain range here.
Yeah.
So you can see the mountain range here.
Yeah.
And the tunnel runs through here.
Mm-hmm.
And there's another one that goes underground here.
What is Goddard Tunnel?
So it's just a tunnel
In
through a mountain in
Switzerland.
Switzerland.
Oh, cool.
Switzerland.
Yeah. Yeah.
I think 2 kilometers under the...
Right.
So interesting.
Again, in using the nomenclature from the first paper, transparent like a crystal, this is what I would want to see.
Okay.
Yeah, it's beautiful.
And again, it was just frustrating for me when I was going through this.
Geoffrey, I will do.
Yeah. So if you can come to the table with something like that, I think that would silence a lot of the haters. So debunking is an attempt to disprove. So when somebody is a debunker, they're trying to say SAR technology is fake because of X, Y, and Z reasons.
Yes.
So that's debunking. And there's a lot of people that have attempted to debunk this, to say it's fake. And then there's the other side where people absolutely love it and they really believe it. So that's what we mean by debunking. And again, that's not what I'm here to do. Clearly, I'm interested and I'm fascinated by this. And I have a vested interest in knowing the truth.
Yeah, we should come up with a new term, which is stress testing. It's not debunking. It's, if there is a there, then you try it under all conditions. Constructively stress testing in a positive way, which I think we're doing here. So, yeah.
So again, this is another image of the tunnel going through here.
Wow.
Again, the reason I showed these is because
you see it very well,
this is supposed to be the proof of concept for the new scanning, but it looks so much different that there's a contradiction between the quality of this and then what is shown.
Geoffrey,
I know you understand it. Yeah. Of course, right?
I think
But all of us want to see this, especially the people that don't believe in this technology.
Yeah.
You have to go back and do it again.
You do. And seriously, come up with a number, and like I will rally, Geoffrey will rally, everybody with the platform will rally to just crowdfund you the money. Let's try. We'll get you the money somehow. I mean, it's so important.
We will do it.
Yeah, because it's on you though to come up with a number, come up with a figure, and we'll get. It's really important.
So this is the rest of the presentation is just going into their presentation during Malta when they're showing the new scans from inside the Khafre Pyramid. We already talked about the azimuth compression. This is the scan of the Osiris shaft. Okay, so this was another proof of concept, scanning a known structure to show that their technology is able to pick up the configuration that we absolutely know is there.
But here we're back to the kind of lower res
correct
scans.
Yeah.
So that is a good sign of validation.
Yeah. So there's
validation.
been some issues proposed with this.
Okay.
So this is from a channel called Night Scarab, who did measurements that show that the signatures are off and that the measurements don't exactly match the known configuration.
What do you say to that,
what was
Filippo?
Because any measurement is affected by errors and aberration. You remember that you are watching things that is propagating in matter.
So you're just saying this is within the margin of error.
It's the best of what we can retrieve today.
What? Sure. But
we are
what?
Not,
yeah, of course.
Gods.
But
we are humans. So
we
have measurements that we have error.
Out of curiosity, what is the margin of error? Like
which kind of the
So he was saying that the measurement,
meters, I think,
4 meters.
4 meters of error.
Which, considering you're measuring from space, using vibrations from underground,
we are measuring
is a relatively.
And you are telling me you made 4 meters of error.
Does anybody argue that the structure overall doesn't comport with the Osiris shaft, or does everybody admit that it basically
the only
matches?
Right? So the only sort of caveat to this scan is this structure over here.
Okay.
So I actually went out to the Giza Plateau after the Malta conference. As soon as we got back, we live in Egypt, so I can go to the Giza Plateau anytime.
I think you found something, no?
Yeah, that's why I was asking you about the footprint, the square meter imaging footprint, the area of the footprint.
The footprint is very good.
It's huge,
But
right?
the
Five
demographic light, here I don't
5 kilometers
remember
by
well.
5 kilometers is a huge footprint.
Yes.
And in the vicinity of the Osiris shaft, so it's located along the causeway, right?
Mhm.
This connector pathway
Mm.
that leads from the Khafre Eastern Temple down to the Valley Temple and Sphinx.
Mm.
And the Osiris shaft is located below the causeway.
Mm.
So directly on top of the causeway, maybe 10 to 15 feet away from the Osiris shaft opening, is another rectangular opening in the causeway that is indicative of another bedrock shaft. There's these big vertical bedrock shafts all along the causeway adjacent to the central pyramid. They're just huge shafts that go down into the bedrock. There is an opening here
Mhm.
at the top of the causeway that goes down into something, but like all of these bedrock shafts, they're completely filled in. It's filled in with sand and
Of
debris.
Mhm.
Debris,
yes.
yeah.
And then now we show some shafts of those that you
Yeah,
are mentioning.
later in the presentation.
Yes.
There's also another structure to the south of the causeway that appears to go underground. That's again why I was asking about the footprint of the area.
Is he measuring any of these?
Who?
Filippo in these scans.
Oh, in terms of the measurements?
Yeah.
Oh, I don't know.
Okay. Because that would be interesting if, like, you knew of something specific around the Osiris shaft that he picked up.
Well, no, that's
or
what
you
I'm
knew of
saying
some-
is we went out there and we found 2 different structures
Yeah.
in the vicinity of the Osiris shaft
Yeah.
that could be creating this signature here.
Okay. Interesting.
So we actually went out, my wife and I.
Yeah. Wow.
Shout out to my wife, Alexa from Archaeology, that's been sitting over there patiently
Shout
watching
out
this whole thing
our
go
one
down.
audience member, live audience.
And this is why we need to go out together. You, me, and Armando
Okay.
need to go to Giza Plateau
we
and
will
look
do
at this stuff so
Yes.
that I know the Giza Plateau like the back of my hand.
Yeah.
And anytime we want to look at a structure, I know where there's anomalies and things like that all over the Giza Plateau that can help us get closer to the truth of what we're looking at here. So I did find some structures that are in the vicinity of the footprint of the scan area that could be producing
That's
this
cool.
signature here on the left. So here on the right, we have level 1, level 2, and level 3.
Mm-hmm.
But then there's also
yeah.
these other horizontal signatures that go all the way down. This one, all of these different horizontal
That is important,
signatures. Filippo, you don't have a conclusive explanation for what's producing this section here.
I want to ask you a question.
Yes.
You know very well the structure of the Osiris shaft.
Yep.
The last floor where you have the swimming pool.
Here. Yes.
Yes. There are some studies, some research that attempt to go and see what there is below the water level.
Have they excavated below the water level?
Or I don't know, they put the camera to see what, or...
No. As far as I know, the only investigation into anomalies inside the Osiris shaft is some connecting tunnels.
Okay.
There are some bedrock tunnels that connect into the Osiris shaft. During the original excavations, they did pump all of the water out.
No, that is impossible.
No, they did.
Ah, they did?
Yeah, they did a pump, and they pumped, maybe not all of it, but they pumped the water out of the Osiris shaft. Yes.
And so the water level was going down?
Correct.
And then, but if they don't pump anymore,
it comes right back up.
In how much time?
Oh, I don't know. But so this was done by Zahi Hawass and team.
Okay.
They pumped all the water out so that they could lift the lid off of the container on the 3rd level.
Okay.
So there's a container on the 3rd level that's surrounded by 4 pillars. It's like a limestone island in the middle of this water with this big container. And they were going down in this thing. It's supposed to be the burial shaft of Osiris. And they're going to lift the lid off of this container and find pharaonic burial or Osiris's body in here. Of course, absolutely nothing was discovered when they lifted the lid of this thing.
Wow.
Okay.
So they did pump the water out. to do this excavation.
And then up.
After the excavation is done, the water level came right back up. Because as I was saying, there's an independent aquifer directly below the structure here.
Yes.
And the third level of the Osiris shaft taps into the water level in this independent aquifer. So everything that we're showing here is underwater.
So nobody knows how deep is the water.
No.
Oh my God.
Yeah.
Okay.
There's never been a hydrological investigation of the depth of the water below the Osiris shaft.
Can I ask a question?
Yeah.
How big the substructures under the Khafre Pyramid that you feel like you're measuring, these columns, hollow tubular structures, what is the circumference?
Yes, I think I don't remember if we have indicated this, but approximately 20 meters.
Each one.
The diameter.
But the diameter of each, sorry, not circumference. What is the diameter?
The diameter approximately 20 meters.
Of each
Yes.
tube.
Yes, and they are and they
Oh,
have
so
a distance of
each-
about 5 meters.
So each tube is 60 feet.
20 meters. I don't remember.
Yeah,
I don't know,
ish.
60.
I mean, that to me, that makes me higher conviction, I have to say. Because, if you're not measuring the Queen's Chamber because of some granite, and it's too small or whatever, I guess the granite actually helps as far as, yeah. So if you're not measuring the Queen's Chamber because it's too small, and then you have this possible, error margin here displayed in the Osiris shaft, that's 4 meters.
Yeah.
I do think if you have a 20-meter single column and then that's repeating 4 plus 4, 8 times, that somehow feels like the only thing, if I were in his position, I could say pretty confidently, and again, we have to get into can you penetrate below
So let's
the earth? Can you penetrate
let's
below
get to that,
limestone?
because
But-
I have a pressing question that
Yes.
I'd like
So
for you to answer.
I'm here.
So everyone's seen. So this is some of the raw data
Yep.
of their scan of the third pyramid, the Menkaure pyramid,
How nice is this?
showing these vertical signatures below the Menkaure
Yes.
pyramid. Same thing here. These are more of the vertical signatures of these structures below the ground.
Hmm.
Same thing here, Pyramid of Menkaure.
Yeah.
There's this big signature here of a possible vertical something below the structure. Here is the model
Yeah.
that they presented at the end of the Malta conference, showing the entire Giza Plateau and these underground vertical features connected into these cube features. The whole model here. So this gets into the question of the water level.
Some of the tubular structures are under the Sphinx as well? That you measured?
Yes, we have measured. I don't know if we have the slide here. Yes, but
Yeah.
the answer is yes.
So here on the left, in the data,
Yeah.
you said that when the image
See,
tapers
look,
off
you have
here.
a cutoff of energy. We discussed it in
Yeah,
part
yeah,
about this.
Yeah, so I'm just explaining to the people.
Yeah.
So on the data here in these vertical columns,
Yeah.
where the data starts to taper off
Yeah.
is an indication of the water level.
Okay.
Okay. And that's reflected in the model.
Could be the indication of the
Okay.
water level, but is not the water level is not present abruptly. Do this experiment. Take a dry sponge, dig a hole on the dry sponge. So you have the dry sponge and the hole on the dry sponge.
Mhm.
Okay? You put the dry sponge here or into a container and you put water. You will see that the water goes into the sponge. And for gravity, the water will stabilize somewhere. But the layer that represents the dry part of the sponge and the more wet part of the sponge is not abrupt. But you have
The
this
transition. Right.
transition.
Yeah. Okay. Yeah.
Okay.
So the permeation of the water
Yeah.
is not linear.
Yeah, it's not
It depends on the absorption of the material.
abrupt.
Right.
abrupt,
Right. Okay.
Okay.
Yes.
So I don't know. That is a strange effect that as we discussed before, I can't give you an exact answer
Okay.
to that phenomena
Okay.
because I don't know.
Okay. And that was my question, is the water level in the model
Yeah.
and in the data is approximately a kilometer down.
But this is not true.
Correct.
Because
So that's
the water level is there. It is.
That's the next point.
Yeah.
Is that the actual water level
Yeah.
below the water table of the Giza Plateau
Yeah.
is shown to be approximately 50 meters
50 meters
below
not,
the plateau.
1 kilometer, not half
Correct.
kilometer. I don't
Is
know.
it 15 or 50?
So it's 15 meters above sea level, 50 meters below the plateau.
Got it.
Right.
Yeah,
So this is
got it.
courtesy of ancient architects, another individual in the community who basically debunked the study.
He's a debunker, no?
He's a debunker.
Okay.
Yes. Yeah. So again, I was just curious, what was your explanation for the difference of the
No.
water level shown here?
The water
And
level, I tell you, can
It's much higher.
you can see it from this tomography.
Here?
Yes.
This line?
Approximately.
Okay, so it's
But they are
not
not
where the
15
image.
meters. You can see something related to the water level. Okay?
Okay.
And
So
it's not that, but it's that one.
So
go,
the tapering of the image here is not because of the water level.
Maybe effectively, if you have an effective physical cutoff of something, and then they continue with another kind of structure.
So this is, I think this is
I don't know. If you ask me why is it like that,
yeah,
you have to go and see effectively.
sure.
The measurements are those.
Right. So what you're saying is that this is supposed to be a solid object.
Yes.
Going more
Down.
than a kilometer
Yeah.
down and connecting into
It's
these
very
large
deep.
cubes.
It's very deep.
However, the signature of this solid object
Yes.
does
changes.
changes significantly.
Yes, significantly.
The explanation you had given in Malta
Yeah.
was because that the water level was here, but we both agree that this is not the water level that's causing the
maybe is
here.
Is there.
Yeah, this blue line.
Yeah,
right?
It's that one.
So if this is a solid object, what is creating the lack of signature here?
I don't know.
Does the lack of signature start a kilometer down, or how many meters down is that kind of cutoff where it starts to go from?
Approximately 600.
Okay, so I guess then if I was you, why?
Maybe there is something that I was, but I can't disclose it now. There is something. I can't disclose it now.
Interesting. Okay. But is there a reason you're saying 600 meters? But like, why did you say it goes a kilometer deep?
Yes, look how nice it is.
Yeah,
You can see that cutoff.
I do see that it maintains
using different sensors. You see the same cutoff.
Yeah.
Like that.
But that's what I'm
It's
wondering.
interesting.
Why are we saying a kilometer deep instead of 600 meters deep?
I don't.
Well,
can
that
you
was just
read
my
it? Can you
estimate.
read it?
So
No,
this,
but it was his
Because I don't-
estimate.
Maybe I am saying something wrong.
Yeah.
The vertical numbers, you can read it. You can read.
so again here. So they're getting a cutoff. So this is
550 meters.
Yeah, so this is
Okay.
600
Below.
meters here. So this is
550.
where the image itself and whatever this is, the signature of this starts to cut off
Okay.
here.
But
See.
there it looks like it cuts off less and does extend
It
down
depends
to
on the tomographic
close to a
line.
kilometer.
It depends on the processing procedure that we are doing. It depends.
Okay. Hundreds of meters,
Yeah.
you would say confidently, and then you don't know what to attribute,
No,
to Geoffrey's point, that sort of awkward gradient. You don't know.
because now we agree together that the water level is higher,
Sure.
and you have a cutoff of the signal. Look.
Yeah, and all of these
Yeah.
vertical signatures
Mm.
show a tapering of the signature.
Mm-mm.
So that's an anomaly of these vertical signatures that we don't have a good explanation for. If this is a solid object, why doesn't the signature register all the way down? It's not, we've agreed, it's not a result of the water table. There's something else happening with the signature where it's possibly no longer able to detect that deep.
Well, do you have an alternative hypothesis or?
So again, at this stage, I'm just asking questions.
Yep.
Maybe we are focusing the attention on something that it is normal to have that kind of result.
Do you see an attenuation of signal?
No, only here.
Okay, only here. So there is something idiosyncratic, unique here going on. Okay, that's interesting.
Yeah. So we can see it here in this polarized tomographic image. This is again the vertical signatures.
I will say the polarized tomographic image, even the raw tomographic image,
Nice.
It's better.
Super nice. Those
better.
look very tubular and like,
same thing here. It has that same. The deeper it goes.
Even when you get that awkward kind of gradient cutoff, like it still looks like it's maintaining some sort of structure.
Look, the water levels.
This up at the top.
Yeah. Got it. Okay. So you, Filippo, would you admit now that you didn't know about exactly where the water level was back then, or?
No.
Okay.
We can make mistakes. No?
Sure.
Yeah,
of course.
probably is the water level, but no, because the water level is now
It's much much higher.
Can I ask
a
a dumb question?
Yes.
Because a lot of this is prefaced on this idea of these structures being man-made and artificial. And so, two questions.
Oh my God!
You don't know.
No, we don't know.
We don't know. But they,
No,
at least a lot of the speculation around them is around.
In my best
them being,
opinion, they are man-made.
but if it's an artificial structure, how would you build something that penetrates that deeply into the water table?
And you asked to me?
Yeah.
Okay, you are asking me this?
Yeah.
Oh,
Have you
nice.
speculated about that? I mean, you have to have thought of it, or
It is something that I discussed about this issue with Corrado.
okay.
And we agree that it is something that it is man-made. Okay, so somebody built those things there.
Mm-hmm.
It can be that once the pyramids were built, so from the top, maybe they dig it on the bottom, but they are not simply holes. They are built. How can I say?
But if they're 20 meters in diameter and they're going a kilometer deep,
Yes.
then I'm going with aliens. like how do we explain that? That's pretty.
I knew
that feels harder to explain than the construction of the pyramids themselves, which are really hard to explain.
Yeah, but so that's the problem, though, is that's where this disintegrates from an academic conversation regarding the actual data to the leap of speculation into alien constructions, which is why the academic community has outright rejected this whole thing, because there's no physical way that these could possibly have been built, period. There's no way.
Yeah, but you would say the same thing about the pyramid.
We don't understand. Well, I agree with you there.
Yeah.
We still don't understand the mechanisms of operation.
Yeah.
But it's also a completely different conversation building something above ground when we're talking about how could you even excavate into the bedrock to be able to build something. It's the logistics of the engineering. So we were talking kind of off camera how the civilization that built the pyramids and associated structures were absolutely able to build components that tap into the existing water level. The Osirion is excavated from the bedrock and constructed to tap directly into the water table below the structure. The configuration of the temple structure is precisely designed so that it hits that water table, again, an independent aquifer that's not connected to the Nile River, because the water level inside the Osirion is the same as it was in the original design, the island and the reservoir surrounding the island. Same thing with the Osiris shaft. They were capable of building structures that go down to the water level and tap into the water level. Now we're talking about going a kilometer below the water level to excavate. The whole thing is filled with water. If they are real, I have a difficult time accepting that there is such a thing that is a man-made structure that goes a kilometer deep. However, the Giza Plateau is the bottom of an ocean from millions of years ago. The Tethys Sea. Are you familiar with the formation of the Giza Plateau?
Sì.
Right? It used to be the bottom of an ocean millions of years ago. And there is evidence of hydrothermal mineral deposits on the Giza Plateau. So hydrothermal vents are vertical structures that can go kilometers deep into the bedrock.
Whoa.
So we can talk about this here in just a second. I want to walk through one more piece of data. So we've talked to...
Well, can I ask one more question?
Yeah.
Because it's very related to the logistics of being able to build something that penetrates a kilometer deep. And this is a flint dibble point. Is it too hot down there?
Yes.
Remember?
Yes, we have to speak about this. It is very simple to give you an answer. The first thing is, it is normal that people could be there. Maybe you can build, yes, to build these structures, people has to go down. Yes, that's true. But there are a lot of methods to cool down high temperature. The first one is this: the enormous quantity of shafts that are present on the surface of the Giza Plateau, that are filled with debris. And one of those, I show them in the presentation. I don't know if you extrapolate.
I have that in here too, yeah.
There are a lot of shafts, and the shafts can have the function of giving air, giving light, and so cooling the underground structures that are below. So the answer is, okay, we want to build something like that. Yes, let's begin building this thing, this mega structure here by digging and building the cooling shafts. Okay, we start from the shafts. Then once we are downstairs there, we intercept maybe natural horizontal cavities, okay? And so we build and we start to build. In some way they did it. In some way somebody did these things. So the vertical shafts that you find principally between the Sphinx and the Khafre Pyramid, there are 4 or 5 shafts that are blocked by debris, and those facilities we are thinking to submit a proposal to the Egyptian government, because those shafts can be the entrance of the underground facility without doing any kind of drill. We don't have to drill.
Yeah.
We only have to clean.
Amazing.
We only have to clean enough.
Well, I hope you get that approval. I guess another question I would have is, are all of the tubular structures a kilometer deep? The ones under the Sphinx as well, they all are hundreds of meters deep.
I have the slide. Yes, because had to transport fresh air and light into the below the structures that are below. Yes, and I tell you, those tag 47, 31. Yes, those.
So this is the causeway here.
Yes.
Right. So we're talking about the Osiris shaft being located on the causeway.
Yeah.
And these bedrock vertical shafts are adjacent to the causeway on both sides. So there's some over here on this side and some on the southern side that go down vertically into the bedrock to an unknown depth. They've never been fully excavated. They were filled with debris and sand. Now also trash accumulation for,
plastic
decades and all sorts of stuff. Just completely filled in with junk.
Yeah. All the tires there are of
and there
is rubbish.
So there's evidence, even just looking down into these vertical pits, there's evidence of transverse horizontal shafts. So
I detected.
yeah.
So
They showed that. So these shafts go down vertically into the bedrock, and then there's horizontal transverse connecting shafts that link these things. So in my opinion, that's part of the industrial infrastructure of the Giza Plateau. And I have a slide on that here in just a sec. So the other pressing question, Filippo, I know you know this was coming, and this is kind of the last question I have for you.
Yeah.
So this is the data of the scan of the Khafre Pyramid. And the big objection is the fact that the known chambers are not shown on the data. So this is above the Belzoni chamber here, and the known chambers should be somewhere down here.
Yes.
So this is the configuration of the Khafre Pyramid, the known internal chambers. And all of these areas that are marked with hash marks here are bedrock excavated chambers. So they're carved directly from the bedrock of the Giza Plateau. And this was the statement. I don't know if you wrote this or if Armando wrote this, but so it states here that the detection issues related to the known structures inside the Khafre Pyramid. The satellite data only reveals the entrance, descending corridor, and the roof. This is because the structures are embedded in a limestone slab that absorbs the signal. So this is the bedrock of the Giza Plateau from which these chambers are excavated. This is no deeper than 15 meters into the bedrock. And the radar signal is absorbed in that limestone bedrock, according to the quote from your team. Again, I think probably Armando wrote this. I don't know if you wrote this, but this was published on the Facebook page. So can you clarify why the signal is being absorbed in this bedrock, and then how, if it's absorbed in 15 meters of bedrock here, how can it possibly scan any deeper?
Okay, yes. The answer is this. Let's start from this matter of fact. We are not detecting the Belzoni, we are not detecting the narrow corridors. Yes, the narrow corridors, because in that tomographic line that we are using, they are not present.
Okay.
So now we are dealing this problem, being aware that sometimes targets are not detected. In this case, we think that exactly what that message was. We wrote that message because the most part of the vibrational energy in that case were attenuated a lot the signal, so we would not be able to retrieve the Belzoni chamber and also other corridors because no energy. We failed the detection of those known chambers.
Okay.
But then
Go ahead.
the next logical question is,
Yes.
if you're saying that the signal is getting absorbed and attenuated
Yes, but-
because of limestone that's just 15 meters deep, then why
How you are detecting those
a kilometer
structures
deep
yeah.
through the same limestone?
Yes. It is a question of measurements. In those measurements, we were not able to retrieve those structures. Okay. But considering the particular configuration of those huge tubes descending approximately for more than 1 kilometer, having a diameter of approximately 20 meters, we can see that they are very big. Okay, so you are comparing a very small object with huge structures. So I don't think that this is a point of comparison, a good comparison point, because you are comparing huge structures with something very small. So in this case, the very small things are not detected. And that's a matter of fact. You ask me why, we gave that explanation. Okay? Because the bedrock, we don't have the vibration, we don't have the vibration, but we have the vibrations to detect the huge structure. And we have detected the things very clear. That's the answer. It is obvious that this work, we have to continue to do this work. So we have to continue to scan the Khafre Pyramid. And so I am sure that we will find results that show us also the Belzoni chamber.
You got to bring
Yeah.
the Gran Sasso improved methodology and do it again.
We need it. Yeah.
This, Filippo, this is critical because, again, to say that the energy and the micro vibrations are absorbed in bedrock 15 meters deep, the deeper you go, the more bedrock there is. And the more bedrock there is to prevent these vibrations from being detected. So it's a big issue. And this is the biggest objection that's been proposed in the community is this bedrock excavated chamber.
There is also another thing that I have to explain you. Why there are things that are very visible and things that are difficult to be detected. It is a question of measurements. Sometimes things are invisible, sometimes things are very visible, are very bright. We found that if things are anchored on the surface of the earth, anchored, so they start from the surface, like the pyramid, like that, like we see it very, very clear because the evanescent waves are very energetically on the boundary, so on the surface of the earth. In that case, the shafts are directly connected to the surface of the earth. So why the surface vibrates, we can detect the vibrations. In that case, the Belzoni is something that is not directly connected. I would say it's there, yes. So we need to scan it more and more.
Have you tried doing these scans on any other limestone bedrock specifically?
Yes, we have the shafts.
The Osiris shaft.
Yeah, and the shafts, but also the vertical
How
shafts.
deep are those?
So we don't know how deep they go. He shows that they're going down
we know.
hundreds of meters.
Yes.
According to the scans. Yeah.
And those are anchored on the surface of the earth, so we can see it.
So the opening of the shaft is actually on the surface.
On the surface.
So you can look down directly into the shaft and see that it goes down into the bedrock. So that reminded me of a good point. So another thing we need is control samples. So for example, you provided really good proof of concept in the scanning of the tunnels and the physics laboratory. Those are fantastic. Another thing that we don't have in the studies are control samples. For example,
I have mines.
No. So scan a structure just like a hill where there is nothing there.
Okay.
Yeah.
To show us a control sample comparison.
We can do it, yes.
Yeah, so that people can see. So this hill, we're going to scan the hill and show what is inside of a hill where we know there's nothing inside and we know there's no big vertical. So this has been another big criticism, is that there's no control sample comparison.
We will do it, yes. We can do it.
So this is also important. In a scientific study, you always want to have a control sample so that you can compare the control sample to the test sample.
Can I just ask because this touches on what you're asking? In the context, these commercial contexts where you're under NDA, you don't need to talk about any of the specifics, but I would just ask you, how many instances are there of these? Because it's not a perfect control like, Jeff is sort of describing here, but it is somewhat of a control where you're looking for like minerals and other things, and we can kind of pattern match like regular land versus these megalithic archaeological sites.
Yeah.
So do you know like how many times have you done this roughly?
What?
If you had to estimate, just the method.
The
Scanning like on anything, like
okay.
is it between 100 and 1,000, between 1,000 and 10,000?
How many sites?
Yeah,
Different
how many
sites.
different sites? Yeah, it's a
Okay.
better question.
Beh, not a lot, about 10.
About 10.
Yes.
Okay, got it.
Not a lot.
Okay.
But they're sufficient to show things where are present, let's say mines,
Mm-hmm.
so tunnels inside, tunnels,
Yeah. And we're both assuming
things that are more controlled where nothing is present.
and we're
So you have difference.
yeah. And we're assuming you've never seen anything like this. Anything like these column like 20-meter,
The
columns diameter
are present because you see signatures that are devastating. You see those columns. What are those?
Are there other times where they've missed structures that are more suspended and not tied to the foundational bedrock of the earth?
Okay.
Are there other examples of that where they missed?
Yes. I
Yeah.
have it. I have
Okay.
those kind of yes.
It's exciting.
But the
because-
experience
yeah.
that's if if these things are anchored on the surface of the earth is better.
Yeah.
I
No,
can
it
see
makes sense.
them better.
I mean, this is exciting because it's the way I net out is like you got a lot of work to do, but I don't think anything's conclusive in either direction. I think you got to just keep going.
It's
'cause
something
there's,
new.
like,
It
more
is
to-
something
Yeah,
new,
that's kind of
and-
my conclusion.
Yeah.
So all the question, and thank you for your
Of
questions.
course, yeah.
Yeah.
I care
gave
about
me-
this, Filippo. This is important.
I tried
Yeah.
to
Yeah,
give
clearly.
you the best answer.
Yeah.
So in the position that I am now, I am a bit tired because of the jet lag. of
No,
the weather.
understandably. You should
And
get
maybe this last issue, this is an issue that of the Belzoni. I am thinking always of the Belzoni.
Yes.
We will solve it.
Yeah.
So it has to be investigated.
Yeah.
But we solve also this issue. So the issue is why we are not watching the Belzoni. At the moment, what you read is the best answer that we can give you.
Right.
now.
Right. Yeah.
But I will ensure you that more scans will be done on the Khafre in order to find something to detect Belzoni.
Okay. So I know you have a big day tomorrow,
Yeah.
and I'll wrap this up quickly just so we can get through this. And I know, we both traveled yesterday, and I'll just kind of cover this briefly. So we're talking about Luis Alvarez.
Yep. I see that.
Just one thing about the vertical shafts.
Yes.
Mhm.
The vertical shafts are very important. I don't know why nobody went there to excavate, to clean. I'm sorry.
The
Why?
bedrock shafts. Yeah.
Why?
There's also
Eh.
no good archaeological explanation for what those shafts are for.
Okay.
From the pharaonic burial perspective,
Okay.
archaeology and Egyptology does not have a good explanation
Okay.
for those vertical bedrock shafts adjacent to the
I tell you
causeway.
this.
Stay
Geoffrey.
tuned.
Some of them are burials
Yeah.
where they've found smaller ones, and they've found bodies
Yeah.
down inside of these because there have been a plethora of burials discovered on the Giza Plateau, not in the pyramids, but in structures adjacent to the
Yeah.
pyramid structures.
Yeah.
So they have found intrusive burials in some of these shafts, but there's not a good consensus for why these things are there. So they've never excavated them.
They made it after the original construction. Those
Sure,
things.
that's another question is which came first?
Yeah.
And are those bedrock shafts an original part, or are they part of the dynastic era construction? So that's always a problem when looking at the layers of
And
building and construction in Egypt.
you observed from the internal those shafts,
Yeah.
and I think that you believe me that are made with squared constructions, one on each other, like that goes down.
Going down into
Yeah.
the bedrock. Yes.
And I tell you that for me, the shafts are waterproof. it means that the water level, if you can see the water level
Mhm.
that is outside the shafts,
Right.
the water is not able to go inside the shafts.
Yeah.
So if we clean the shafts,
Yep.
we always find air, not water. Also, we go below a lot. Okay, I don't know if you agree with my idea.
Yes, because that also fits with my hypothesis
Okay.
on the function of those systems.
Yes.
So that would get us into another hour-long discussion on. So you and
Next time.
I should sit down and talk about the function of everything sometime.
And so the project proposal that we are we are thinking to submit these weeks. We are involving University of Ferrara. We are involving other academic organizations.
Yeah.
I am out of this project because it's better that I will remain out. And our intention is to use robots, not humans, because it's dangerous to go there.
Yeah.
To use robots and clean the shafts.
Yeah.
I don't know.
They should do that anyway.
Yes.
Because of all the trash.
Yes. Let's say we can go below 1, 2, 5 meters a day. Okay.
Yeah.
We just begin to work and every day we go.
Yeah, absolutely. So this next thing, I mentioned that there was a muon scanning of the central pyramid. Luis Alvarez, I knew I recognized the name, so he was a part of this. They scanned the Belzoni chamber and the area above the Belzoni chamber. They didn't find anything.
Mm-hmm.
So they scanned approximately 19% of the total volume in an area here that was a cone half angle of 35 degrees from the vertical. So it's this cone that they scanned above the Belzoni chamber.
Okay.
And they didn't find anything.
Mm-hmm.
These are also supposedly located directly above the Belzoni chamber. And we've already kind of had a back and forth discussion about which is the most viable detection method, muon scanning or SAR scanning. Muon scanning says there's nothing. SAR is now detecting something.
Yes.
So again, we don't have to get into a labored discussion about, who's right and who's wrong.
No, it's better that they work together.
Yeah.
Maybe in this case, Muon, the old version of Muon, because that's a paper
from the 70s. Yeah.
The 70s.
Yeah.
Maybe in that, and I am not criticizing Muons because they are fantastic. Maybe in that time they are detecting nothing on a 35% of aperture.
Correct.
Do you have an explanation though for why they didn't detect anything above the Belzoni chamber and you did detect something?
I tell you why. Because as now we know that the Muon scanning are detecting things that is the sum of everything you are watching on the top. Is the sum like that. And so it is difficult for me to see things, facilities, when you are watching the sum of everything. You saw 50 years later that paper, so now the modern Muon detectors, it is highly probability that they are saying that there is a big void on the Grand Gallery, which is parallel, but in my personal opinion, are watching the top and the bottom and the roof and the floor of the big gallery, of the Grand Gallery.
Yeah.
Like that. Look, they're watching this and that. It means that the technique fails sometimes. And it failed. Maybe it failed also 50 years ago, in the period of when that paper was written, using old detectors. Who knows? There is something that happened, and they are detecting nothing.
Yeah, and I don't know that any recent muon scanning has been done inside the central pyramid. So they need to go back and do it again.
Yeah. They have to do it again.
Yeah.
Why they didn't install detectors inside the Belzoni?
Right.
Right.
No?
Yeah. It's a good question.
So just kind of a final note. That was the end of my questions
Yes.
for the SAR project. And Filippo, I think you did a really, really good job today
Thank you.
in answering to the best,
The best
of your ability.
that I could.
Absolutely. Yeah. Sure.
make.
Agreed.
So the final note here is just a mention of these hydrothermal veins
Yes.
and iron ore deposits. So here I'm standing
Look
in
how
the
nice
middle.
This photo. Look how nice it is.
Oh, thank you.
There you can find the floor of the Giza Plateau where the pyramids are on.
Yes.
Those. Look.
So this is bedrock here.
Yeah.
This
But
is
it's man-made.
limestone
It is
paving.
man-made.
This part here is man-made.
It's man-made.
This part here.
Yeah.
This is bedrock. Limestone bedrock
Yeah.
that's permeated with iron ore deposits, metal ore minerals, which is directly applicable to the utilization of your technology
See.
for finding
See.
metal ore mineral deposits. So this is where these two things have a synergy that I think we need to look at further. So here I'm down inside of one of these quote unquote boat pits.
Mhm.
And this is an image
This
of
is a tube, a metal tube.
metal tube. Correct.
Yes,
It's
that's a
an
metal tube.
it's an iron
I saw it. It's a metal tube.
it's an iron ore
Yeah.
vein.
Yeah.
Yeah. So these are you've never seen this before.
That's wild.
So this is about 1.5 feet long
Uh-huh.
and 1 foot deep, and it's a tube
Yeah.
of iron ore.
Cool.
And these veins run all through the Giza Plateau.
Whoa.
Yes.
They are hydrothermal metal ore mineral deposits that are embedded in the limestone bedrock of the Giza Plateau.
Whoa.
So these are the result of hydrothermal vent systems, seafloor hydrothermal vents that push these metal minerals up from the earth, and then they deposit them on the surface and inside the layers of the bedrock. That's how these things form. So here in red, I have depicted these vertical bedrock shafts adjacent to the causeway and the interconnecting transverse shafts. So you can actually look down in this, about 20 meters down, and you can see the transverse connecting shafts that aren't that deep. Here we have what Filippo's team is showing, which could be the remnants of some of these hydrothermal mineral vents, these hydrothermal vents coming out from the bedrock with the magma chamber. So again, there's magma down here, which could be these cubic type formations, huge geological formations that are known to go down kilometers into the bedrock.
Very
So,
interesting. It's
What do you
really
think
nice.
about that theory?
It is a theory. I accept it absolutely. Like I accept very well the theory of Christopher Dunn and the theory of Geoffrey.
Yeah.
We have to collaborate all and see effectively what there is and which is the effective purpose of the Giza Plateau.
Exactly.
It can be not only mine or yours or also the sum
Of course.
multiple purposes.
Sure.
No?
Yeah.
Something like that.
And I think that understanding the impetus for choosing Giza
Yeah.
is critical in understanding the overall function of the Giza Plateau
Yeah.
because we have hydrothermal vents, we have metal ore mineral deposits, and in this paper, they've also shown that there is a karst cave and tunnel system that is the source of hydrogen sulfide gas coming up from the Giza Plateau. So there's caves and tunnels all throughout the
Natural.
Giza Plateau, natural, that you can also see produce these vertical features located directly below the Giza Plateau. And my hypothesis for the function of the Great Pyramid is that the hydrogen sulfide gas coming from this subterranean karst cave and tunnel system is the initial reactant in the chemical manufacturing sequence within the Great Pyramid. So they picked the Giza Plateau specifically because of all of these features in the bedrock, the metal, the hydrothermal vents, all of it works in conjunction with the system above ground.
Yeah.
So there is absolutely something below the Giza Plateau located directly below the pyramids.
What would you do with the hydrogen sulfide?
Convert it into sulfuric acid.
And what would you do with the sulfuric acid?
Sulfuric acid can be used for fertilizer applications, but also specifically for mining and metallurgy.
Got it.
Because we have a huge supply of metal ore directly on the Giza Plateau.
So agriculture and mining and metallurgy. Interesting.
Also gold mining, no? Right.
So the samples of the iron ore deposits on the Giza Plateau also contain gold, silver, electrum, precious metals, rare earth elements, everything that you could think of. We'll talk about it.
Love it.
I have all the sample analysis data.
This is the perfect cliffhanger to end on.
And also, there is also electricity inside this.
So in the veins,
Also,
we also
Christopher
found
has his,
fulgurites, fossilized lightning.
Okay.
In these iron ore veins,
Whoa.
we have samples that contain fulgurites, which is evidence of high voltage electric current distribution through these iron veins. We'll get into it tomorrow.
Oh, wow. Okay. Well, what a cliffhanger.
I think we have to do another.
Yeah, we do.
Yeah.
Seriously. No, but this has been amazing. Geoffrey, really appreciate your
My
questions.
pleasure.
You asked just really detailed first principles questions, but that were very respectful. And I think this was just this beautiful exploration. And Filippo, I can't say enough about how just open you are to fielding these sorts of questions. A lot of people get very precious about their theories and they don't let them be questioned. And
Thank you for these questions.
You're clearly not that. You're clearly open to updating
Yeah.
your own hypotheses, beliefs. And I think we have a lot of action items here. I think maybe the biggest one is getting those thinly sliced, what you did with the Gran Sasso, but for, the structures underneath the Khafre Pyramid. But this was amazing, and I appreciate you both.
Thank you.
All right.
Awesome.